So we're going to talk more about music today, and we're going to go through some projects and studies that try to establish a rigorous neuro-computational foundation of musical learning and enjoyment. I'm Gert Pelofi, for those who don't know me, and I work in the field of music neuroscience at NYU. So first we could, I don't need to ask myself this question, but maybe some people in the room would like to know, why should we care about music perception? And there are a few elements that we can just point out right away. So one is that music has been around for a very, very long time and seems to be one of the oldest landmarks of music, of human cognition and humankind, let's say. So there is traces of instruments, musical instruments that trace back to 40,000 years ago, such as this one that has been found in Germany. It's also known that music is found across the entire surface of the globe in one shape, in different shapes or forms, but still as a unified phenomenon. And finally, we can point out also that music seems to be playing a relevant and important role in our social activities in those different cultures. We can also point out to the fact that it's a massive industry with revenues, in the order of several tens of billions in recorded music, music publishing, and live music. And finally, it's also a very potent clinical tool, and there are many studies discussing the result that have been gathered around the benefits of music therapy for Alzheimer's disease, or stress reduction, or has to do with as well sleep quality, but also, anxiety, autism spectrum disorder, Parkinson's disease, post-stroke recovery, hypertension, you name it. Finally, and that I find a very striking and interesting argument, music found its way in the Voyager Golden Record, which was sent by the Nazi. It's the second time that I do that. The NASA. Not the Nazi. Try to avoid. And which is now the furthest object from Earth at the present time. And this record has been engraved with some of the most significant artifacts of human creativity and humankind. And it's meant to be maybe discovered at some point by the aliens. And in this record, it was engraved several pieces of music from all over the world. So I think that also speaks volume about how important music is to represent who we are as humans. Now, a little note about why music perception is so interesting from a neuroscience point of view. And that starts with the idea that music is structured sound. And now we're going to see if music is going to play, and I hope it does, because otherwise the whole talk is going to fall flat. Okay. We have no music. Is there any speakers?
What, when you shared your audio from Zoom, you said
I did do that. I shared music when I did sound.
Yeah. And so one thing you can temporarily do, actually I don't know what we can temporarily do. Mute the room speaker, and then crank up the volume on your laptop.
Mute the room speaker. So this one?
The microphone.
Yeah. Not the microphone, the actual, reduce the volume. Maybe the microphone, maybe both.
Okay.
Because it's kind of important to your talk.
Sorry. And now? I mute my computer, it doesn't work. I have to unmute, and so there's going to be a bit of an echo. But anyways, you guys get the idea. So this is the idea that music is structure sound. As you can see here, you have a representation of a piano roll. That's not though. That's okay. Of a piano roll with a frequency axis and axis and a time axis. And so music is structured along those two primary fundamental dimensions, and these define things such as timbre, but also pitch, which in self, when combined together, define melodies, which themselves define motifs, which themselves group together and structured around defined, musical forms, such as a fugue sonata, or just talking about Western music, but many other types of forms in other cultures as well. And so because of this structured fundamental feature of music, we can apply computational modeling. We can try to apply some models that's going to capture the embedded structure that is quite fascinatingly structured around different timescales in a very elaborate, complex manner. And this computational modeling, we can also, sorry, I'm going to do this. This is loud. We can also use this computational modeling to interface it with other types of models, such as decoding models, with human perception and cognition, and try to understand the ties that there are between human cognition, or cognition at large even, and musical structures. And we're going to dive into this specific question a bit more along the talk. But to just wrap up with this idea of what we should care about music perception, this is just a paper that outlines the many different parts of the brain that are solicited as a network while during just music listening. So you have like the two views of the brain, and basically you can see that there is just so many different types of functions and types of an area of the brains that are recruited in only music listening. Okay. Now getting back to this Voyager Golden Record by the NASA, we can just listen to a few snippets very rapidly just to prove a point that I think is nice to prove with music. So I'm just gonna. So those are excerpts. Ah, shit. Those are excerpts from the.
Maybe if you change the sound, like
I should stop working on music altogether. It's just like.
How the hell are those extraterrestrial people gonna be able to actually hear this?
they
Well,
write
they're
words
supposed
on
You
it.
cannot get it right on Zoom.
We know that by now.
Well,
We hope these people are sharing. Stop sharing.
Yes, to see if change the sound from here. It's not recognized.
Sound setting. What do you want to change? Outputs here.
It's not
Yeah.
recognized because it's not connected. That's the
Oh,
problem.
okay, sorry. We'll have to keep going like that. So how would you? Is it sharing right now? No. There. Where is that?
You can go back with this, the toolbar, so if you move the toolbar.
Yeah. Yeah, sorry. Here, there we go. Okay. So I'm going to insist because music is nice. Nice to listen to it. Okay, let's stop it. This is just music that's very varied in its form and structure, and it's nice to be able to hear it normally, like it should, we should be able to do, but that's not working. So anyways, the point is to say that music is very varied, and and yet we all recognize it as different types of music. So the question is, are there universal features in music? And that has been a very long debate among ethnomusicologists, and luckily, I mean, they made very important contributions, of course, but now we have also some statistical tools and music corporas that can tackle this question from a bit more computationally informed angle. And so there is this paper that was published in 2015 about statistical universal reveal the structure and function of human music. And so this team of researchers took samples of music from literally all across the globe and extracted some information about these music and were able to map the features that were the most recurrent in this table here. So this is how you read it. You have on the top more prevalent and less prevalent features. And what you can see here is that you have these three top rows that really show almost perfect ubiquity. So a very, very high prevalence across all those regions that they looked at. And that begs the question, what are these features serving? What purpose are they serving? And are they carved? Are they constrained by cognitive functions about the way we need to interact with music? You will notice that the third row refers to scale degrees, and it says that musical scales, which is the way the spectrum is divided into discrete pitches or chromas or notes. And those number of notes across the octave is typically less than 7. That's what this result is showing here. So we're going to dive a little bit into the case of musical scales, as it seems to be such a prevalent, interesting feature. And so, as I said, it's the collection of discrete pitch that form melodies. It's an organizing principle that transcends cultural boundaries, as it was already noted by people that were just working with as ethnomusicologists. And on top of that, there is the prevalence of certain scale structures that are non-uniform. And that was the second point. It was a non-equidistant scale. So what they mean by non-uniform scales is that if you represent it here with a log frequency axis at time, so each one would be notes, and so that would be the classic major scale, as Michael Casey showed us. The path is maybe to just sing when you present music, I guess. And so you can see that the spacing between the logarithmic steps on the frequency axis are uneven, as in you have whole steps and half steps, as opposed to a uniform scales that's a bit harder to sing, something like that, which is the idea that you divide the entire octave into uniform intervals. And so basically what has been observed is that there is a very, very large prevalence of non-uniform scales. So here it's the classic major scale that we use in Western culture, but there are many other types of these scales that are non-uniform in different cultures as well. We can represent those scales across the octave span just for easiness of representation. And so that's what we're going to do here. In this study, we designed two scales that were one uniform, composed of half steps, only whole tones, and one non-uniform that was not the major classic major scale, because we wanted to avoid effect of familiarity, but we designed another one that has similar properties. And then we designed a very simple musical grammar made of a one-order Markov chain. So basically, each one of these elements here represents one of the notes drawn, sampled from the scales. And this way, we can generate melodies with these two different types of scales. And during an exposure phase, we took people and we asked them to listen to a bunch of these melodies in two different sessions, one with the uniform scale and one with a non-uniform scale. And in a second part of the study, well, right after the exposure, they were presented with melodies that were either derived from the same grammar as in the exposure, or derived from a grammar that had been altered with grammatical violations, new types of transitions between tones that were not allowed in the exposure. So to create syntactic melodic violations. And we asked people to detect those violations, and also we recorded their EEG when they were doing that. So this is what we find in terms of behavior. If you look at the D prime, we find that they are much more able, oh, sorry. Well, anyway, they're much more able to detect the violations in the case of non-uniform scale. And then when we looked at the EEG, what we did is that we applied this classification algorithm that I presented during the tutorial a couple of days ago, which is basically the idea that you take at each sample time, you look at the best way to separate between conditions. And here the idea is to separate between incorrect melodies and correct melodies. And we applied this analysis for, in the case of the uniform and non-uniform scales. And that's what we found. So this is the accuracy of the decoder over time. So the time being the length of the melody. And what we found is that in the case of the non-uniform scale, around 3 to 4 seconds, we have a high bump in decoding accuracy between incorrect and incorrect melodies, which actually corresponds to the time where the first violations occurs. And when we look at the uniform scale, we didn't find such a bump in accuracy. So meaning that the neural presentation was not able to be separated between incorrect and correct melodies, probably, and echoing the behavioral results. And interestingly, there was a correlation between the D prime, so the behavioral performance, and the separability of the neural representation at the individual level. So these points are individuals for the non-uniform and for the uniform scales. So altogether, this study suggests that there is something fundamental about the structure of scales that better supports melodic learning. And that's why non-uniform scales are much more broadly represented across the world. Now, moving on to a complementary perspective on that, we looked at why there is the prevalence of a certain type of scale in the world, which is called the pentatonic scale, and precisely why the pentatonic scale, as we know it, is represented so broadly across different cultures. So as I said earlier, the classic major scale, for instance, do, re, mi, fa, sol, la, si, do, this is found in some cultures, but mostly in Western classical music. Whereas this pentatonic scale, which is the scale that you obtain when you only hit the black keys of a piano. So how does it go? Oh, I can't sing it, I'm sorry. But anyways, so you get the idea? Yes, this one exactly. So this one is not only found in Western classical music, but also in a vast majority of musical cultures in the world. And interestingly, it's always under this form, because obviously you could form, if it was just a matter of number of elements, you could think, any scale with 5 elements is going to fit this criteria of being, not too complex, not too big. But interestingly, this is the one that we found everywhere, this precise shape structure. So we wondered what was special about it. And to answer this question, we put together a protocol in which we had a random walk across the structure. So here there was no grammar to be learned. It was just random steps between the notes of the scale. And then with this random walk, we designed a probe melody and then 2 test melodies. And in the test melodies, we either swapped 2 of the elements or shifted one of them. And the idea was to ask people to detect which one or to elect which one they thought was more similar to the first one. And this is a way to probe their ability to detect out of set melodies, because the proportion to which they're going to choose the one where we shift represent their ability to immediately detect that there is an out of set note in the melody. So in this experiment, we test precisely, as opposed to the learning of the melody, we test the representation of the scale itself, of the scale as a pitch ensemble, a set ensemble. And what we did is that we generated these melodies with all the possible combinations of 5 tones that we could get from the 12-tone distribution, classical temperament division of the octave. And so you see that here somewhere we have the pentatonic scale, but we also have any sort of weird combination possible. And we looked at the rate in which people chose the shifted versus the swapped melody as a more salient similarity to the exposed melody. And what we see is that there is a wide distribution of responses spanning from where they really prefer the swapped one to when they really prefer the shifted one. And what we found is here at the very end, we have the pentatonic one, which really suggests that for this particular melody, they really preferred to, they really had a very strong anchored representation of the set itself. But you could think that's also just for, you know, familiarity again. But if you look at the one that are just before, you can see some features that seems to be more similar in terms of how they're constructed to the famous pentatonic one than these ones, for instance. And so what we looked at is a particular feature that we called evenness. And it's the fact that the shape of the structure is maximally even, given the constraint, which is to build a scale with 5 elements among 12 ones. And so what we found is that this behavioral effect was correlated with the maximal evenness of the set, and the pentatonic scale being the most even scale that you can build this way. So again, this is an attempt to understand the cognitive constraints that shape the way music is similar across different cultures. Now we're going to turn to another aspect, which is actually linked to all of that in some sense, which is musical expectations. And what do I mean by musical expectations is the idea that when you listen to music, whether you know it or not, but maybe you do, you're actually continuously computing what's coming next. And this is a broad general phenomenon that we know about that's called, it's not called, but it can be looked through the lens of the predictive coding framework, which is the idea that the brain needs to anticipate elements to just compute faster and make less mistakes and allocate resources where it needs to. So this applies to tons of different domains of perception, and including auditory processing and including music perception. So I'm just going to try to play this sequence of harmony just to give you a chance to really think about what your brain is doing when you listen to an harmonic march like that, which is so well structured in terms of the next steps. I don't know if you could hear your brain compute, but it was computing. And here it's based on not only the stuff that you know about classical music, but also just very basic Gestalt principles, because it's a harmonic march. I think so. So it's just a basic, a local context computation that you're doing as well. And interestingly, Leibniz pointed out way before he had any means to really, tackle it computationally, I guess, but he said that music is a hidden arithmetical exercise of a mind unconscious that it's calculating. I find it very interesting. So we may wonder what determines musical expectations, and this is where it gets interesting with what we were talking about before, which is the universal structures of music. But as we said, music is also very diverse, very varied in its structure. And the idea here is that what determines musical expectation, it's precisely these differences across cultures. So music is, not all of it, but a large part of it is organized around sequences of pitch, which we call melodies. It's not necessarily the case, but it's a prevalent feature. And these melodies are organized with syntax that are more or less complex. So in the previous studies, I made a first order Markov chain syntax, but you can imagine that in music, it's a similar type of structure, but with much long higher order of sequences. And so the idea is that when you are exposed to music, you learn these sequences over these different temporal scales, and you use this knowledge to compute what's the next element. And what's interesting is that we end up with people, because they have different exposure, having different expectations. So for instance, here, if I play you this melody, you can imagine different endings. So some people may want to imagine that. Some people may want to imagine that. Which one do you prefer? I like the second one better. But both are valid, right? None of them sounds crazy. And they're just slightly different ways of computing what would be the next element. The first one is more like a resolution, grounded in the resolution also, that's why. Anyway, so what determines musical expectations? It's both the local statistics, as we saw with the sort of march, da, 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 and the harmonic sequence, such as the one that we just looked at with different types of chords. And those are determined by long-term statistics, which are acquired through long-term exposure to a musical culture. And for the case of Westerners, it's long-term knowledge of the tonal system. Here, another music example about why musical expectations are so important. And this is a piece of music, one of my favorites, it's a piano sonata by Schubert. And you will see a rise in tension and a very unexpected moment that's also incredibly beautifully expected at the same time. And this is why musical expectations are so crucial to music. I think that's a good, that exemplifies it well. So I'm gonna go ahead and try to play it. I don't know if you heard that, but there is like a shift in tonality that's extremely audacious, because it's going from C minor to a C major, which sounds like they're close together, but actually in music theory, they're very much apart. And it's quite a feat, and that only someone like Schubert can achieve, to be able to manage expectation this way, to make it sound right, but as well create this shift of light or change in atmosphere so gracefully, seamlessly, and beautifully. So anyway, the point is, musical expectations are the bread and butter of musical pleasure. So composers plays with the listener's expectations to create this musical tension and surprise that creates this, which seems to create these emotions. And studies demonstrate that musical expectation modulate activity in reward regions of the brain. We're gonna come back to that later in the talk. But so no wonder why music expectations are tied to pleasure the way it is. So now the idea, or the question rather, is how do we model musical expectations? One way to do that is through the idiom model that has been put together by Marcus Pierce some almost 20 years ago. And the idea behind the idiom model is to look at the n order sequences of music as an n order Markov chain. So it basically computes the probability of sequences of different orders. So 1, just the note before, 2, 3, 4, 5, etc., simultaneously. And with this sequences, then it can make predictions about upcoming events because it's trained on a corpus. And then when you test a new melody, it's going to look at the probability that he had learned in this corpus, and it's going to make these predictions based on this. And depending on how the music that you test is, you're going to have a prediction that's more or less based similar to the ground truth. So if the music is very similar to the type of music you train your model on, obviously you're going to have predictions that are more, more similar to the ground truth. And this way you can derive by comparing the prediction with the ground truth. So the probability of the note that was predicted with the actual note that was predicted. Well, sorry, you take the note that was predicted and you look at the probability that it had in the model. You can define informational content, which is basically the minus logarithm of the probability of this note given all the context. And another interesting feature of this model is that you can also output entropy, which is the ability to predict or the predictability. So think it as how skewed the prediction distribution is. So if you have a very skewed prediction, meaning that there is one main node that's most likely to happen, you're going to have a very low entropy, and you're going to have a high entropy when you have a much flatter distribution. And this is important because it defines the idea of music that are more random to music that are very well structured. And that's important for music cognition, as we will see later. So in this study, what we looked at was the cortical tracking of musical expectations, because in the past, and I'm not going to present that here, but there have been many studies showing that people do compute next elements. And there is many studies showing that with singing, or with people betting, or with people choosing what chord sounds better, just like we did today, for instance. All those sort of things have been conducted in the 80s and 90s and prove that people do make expectations, that they do make them in terms of what they've been exposed before. But this one was one of the first studies to show that we can also track these musical expectations directly from the neural signal. So what we did here is that we use the EDM model to output some melodic expectations features, so the surprisal and the entropy. Don't worry about that, it's just the idea of, we looked at the rhythm and the pitch, but it's just, yeah, you can think it of as a surprisal or information content, being like how much surprising a note is, and the entropy being how much predictability you would have had, how much uncertainty you are about this prediction. And and we took monophonic pieces of music. It was Bach music, but we arranged slightly, and we played it to people while their EEG was recording. And after that, what we did is that we conducted this TRF analysis as in temporal response function. I went through it in the tutorial, but the idea is that you fit a kernel that describes the mapping between a feature, here envelope, but could be any feature, and the neural response, and you train those weights or this kernel on a part of the data, and then you test it on another part of the data. And then you look at the correlation between the predicted EEG and the actual EEG. And the more they're correlated, the better your feature is represented, your regressor is represented in your neural data, your real neural data. So it's an index of cortical tracking, those R values, basically. So that's what, And so the idea here, the hypothesis is that when we were going to run the model with just the acoustical features versus the acoustical plus the syntactic features, we would have a gain that would, in cortical tracking, that would reflect the representation of the musical features in the neural signal. So that's what we found. This is all subject together, and this is the prediction that I talked about, which is this cortical tracking index. And we found that when we looked at the acoustic alone versus the acoustic plus musical, we had a gain in cortical tracking. And the scale makes it not very impressive, but it's significant, and it was reproduced many times after that. And so those are just individual differences. And so just to show that it's something that's consistent across individuals, not just for one or two outliers. The difference is here for most people, and it's sharper for musicians than for non-musicians. And this is just, oh yeah, that was kind of interesting. So this is looking at the difference, the delta air between the music and the acoustic and music when you varied the memory of the model. So it shows that the model captures something that really relates to the neural encoding of music, because if you decay, or if you reduce the memory, then you have less of a good tracking of the surprisal. Just like a cognitive sanity check, if you want. We were also lucky to be able to run these musical samples in patients from Colombia. This was done in collaboration with Nima Mizgarani at Colombia, also Shiab Shama and Giovanni Di Liberto, and who else on this paper? Well, anyways. And so what we did is that, yeah, so there was this patient that, they come for epilepsy usually, and so they have deep, no, in this case, it was ECOG. So they have grids of electrodes on the surface of their cortex. And so this is a way to get very, very clean signal, and also a very precise localization of where the cortical tracking is happening the most. And in this two patients, what we found is that we had an enhanced representation of the musical features in the planum temporale, which is a intermediate level region of auditory processing. And this, interestingly, it was the difference between music and, the gain from the music features was heightened in these regions when compared to lower level regions such as Heschel gyrus, for instance. So again, consistent with the idea that surprisal represents some sort of high order musical features that's encoded in the brain by intermediate levels of processing. Quickly, we tested and replicated this main effect using another model than the idiom model. So if you remember, the idiom model operates on MIDI files. Well, actually, I didn't say it, but it's based on the symbolic representation of music. But music cannot be always expressed in terms of symbolic, well, potentially could, but not definitely not in MIDI files or in MIDI format. So we thought to test this cortical tracking with surprisal with another type of models that not takes MIDI as input, but just the WAV signal. And this was a model developed by Munia Elilali, who was here a little earlier at Johns Hopkins with Benjamin David, sorry, and they did this model based on Bayesian statistics, where they take the music as they take any sounds, but in this case we took music, decomposes it in some features, and calculate the surprisal at each time sample based on the distribution of each feature separately. So you basically have then at the end an output that's a surprisal. We first thought to test the surprisal value against behavioral surprisal, just to make sure it was making sense in terms of how people perceive it. So we asked people to continuously rate surprisal, and we looked at the correlation. And just to make sure, or by curiosity, I guess, we also correlated it against idiom to see whether it was correlated. So somewhat correlated, but also not totally, which is interesting. Probably captures different parts of the way we compute surprise and expectedness. So what we did is that we took people, and actually this is, it was not EEG, it was EEG data, which is another type of electrophysiological signal that you get from the magnetic activity and not the electrical one. So it's more precise in the sense that well, it's the main advantage is that you can also reconstruct the source from the brain, but let's keep that. So the idea is that we took MEG data from people listening to music that was different from the one that was tested before. And we looked at the encoding on envelope, and more precisely, the first derivative of the envelope, which sharpened the onset, and the surprisal as outputted by Muñoz model. And what we found is that, so this is the temporal response, which can be thought as a model ERP for the envelope, and this is the one for the surprisal. And what you see here, if you have a phrenology skills, like Malcolm mocks me, is that you have a little bump here that corresponds to what we call a surprise, or like well, we can call it a P300, but it's basically a signature of higher order cognitive process. And when we looked at the encoding precisely of the surprisal, we did a shuffled model where we shuffled just the surprisal signal, and we found that the real model was better than the surprisal model, showing that really the surprisal is indeed represented into the brain, even when under the form of this Bayesian computed surprisal model. Okay, now we want to look at a more refined aspect, which is the culture-specific expectations. So going back to the idiom model, because it's convenient for that, the idea is that can we use this model to pull out differences in the way people listen to music? So if you remember the example that I gave earlier, people were people make expectations based on several elements, and one big element is their musical exposure. So if they're from the same culture, they're going to be exposed to slightly different things, leading to slightly different predictions. But if they're from vastly different cultures, maybe this prediction is going to be even more apart. And obviously, this is complicated to really implement it because of the pervasiveness of the Western culture in our world. But there is a lot of people that have tried to look into that. And so here is a framework with which we could lead these sort of research threads. So we take the idiom model, you remember this n-order Markov chain, and we train it on different corpuses. So the different corpuses are just a bunch of MIDI files that are from one region of the world versus one other. And so here we chose to run it on a Chinese corpus from the region of Shaanxi. And we chose it because it had been tested before in another paper using idiom, and a European corpus of folk songs. And we matched them for length and complexity. And what we did is that we trained both of them. We trained the model, sorry, with both of them separately. And what we found is that when we tested melodies, we found slightly different predictions. So the predictions of the model when it was trained on the Chinese was outputting slightly, probabilities that were slightly different from the ones. If you like, for instance, compare here or here, this note is strongly predicted by the European model and not this one. And you can actually see it's here. And this is a Western song. So that kind of makes sense. So again, if you remember, if you take the minus log probability of each event, you end up with what we call the information content or the surprisal. And that's just really a way to symbolize or to represent how much each note is expected or unexpected given a certain context. And here the context is the long-term exposure or the culture of people. So for instance, here, because this note is very well predicted by the model, the surprisal is very low, or the IC, the information content. And here it's not well predicted, so it's going to be higher. And just to reiterate, it really is meant to model or to model what's happening in the head of people as they listen to music. So now if we take these outputs and we looked at what happens on Chinese and European songs that are just for test, we can plot this 2D map where on one axis we look at the average reprisal over the melody when the model is trained on the European corpus and when the model is trained on the Chinese corpus. And we can do that with both European and Chinese songs. And what we found is that for the Chinese song, we find that on average, they have a lower surprisal on the Chinese model axis than on the European model axis. And similarly for European songs, so they have a higher surprises on the Chinese model than on the European model axis, which really shows basically that you can use this IDM model to separate, to pull out the cultural features that are present in corpuses. So this gives us a great opportunity to look at learning and to model musical learning. And what I mean by that is that you have this output by the differently trained models, and you have a very high separability that is captured by the structure of the model. And then what you can do is that you can look at how the surprisal decays as the corpus gets bigger and also as it gets exposed to new songs. So if you look at the surprisal for Chinese songs, but you only expose it to European songs, what you observe is that there is a slight progressive decay of the surprisal because it's learning. So it's learning more and more sequences, it's less and less surprise. But that's only when you train it on European music. So that's what would a person trained on the Western music would experience throughout his life if you were to expose it to Chinese songs randomly, right? But now, when you start exposing them to Chinese music, this is what you learn. You see a sharp decay of the surprisal because now it's starting to learn the real statistics that are going to be able to best approximate the predictions. So just to show you that this idiom tool is quite powerful at computationally modeling what may happen in the brain of people. And then, so what we can do then is that we can take the surprisal predicted by both and compare it using TRF, so how well each feature is represented in the neural data. And what we can do is that we can look at a before-after exposure learning curve by, again, placing it into this 2D map that we saw before. And hopefully what we expect is that people that are exposed to Chinese music are going to increase their correlation to the Chinese model, and people that are exposed to Western music would increase it to the Western model. So that's what we thought we implemented in this study. That's in preparation. But we had in a pre-EEG test, then an exposure phase of 2 weeks where people had to listen to at least 1 hour every day on a website, and they were like catch questions to make sure that they were doing it and everything. And then the first post-exposure where they came back and they were exposed to a new set of melodies. And what I didn't say is that in the exposure phase, there was a test group and a control group. The test group was exposed to Chinese melodies only, and the control group was exposed to Western melodies. And in the pre and post exposure was a test of Chinese melodies that was not in the exposure corpus, so completely novel, but of the same culture. And then we had another part of the experiment, but I'm not going to discuss it here, which was that people came home, listened to whatever they wanted, and then came back again just to see if the learning was maintained. But so that's what we have when we look at just the behavior. So we asked people how much they liked each melody that they heard, and we compared from the before and after. And what we see, which is very consistent with previous literature, is that the people that were exposed to Chinese melodies start liking them more. So they enhance their pleasure. And it's going to be important for the next point that I'm going to make. But this is I mean, a replication of what we knew already, but it's always nice to replicate, right? And then we looked at the change in the cortical tracking. So this is the delta R values, looking at post minus pre for test group and control group. And what we found is that we had a significant increase, and it was actually just significant, but we had a significant increase of this delta R for the test group, meaning that their correlation with the model, the Chinese model, increased more than for the control group. And we had not enough participants, probably we had only 15 in each group. So we're actually undergoing more data collection for that. That's just a map of the, I mean, that's more, yeah, anyways, there are some studies that showed that surprisal, if you look at the topography of it, it's kind of situated here in the Mickey Mouse ears. So that's kind of cool that if you look at the difference, you kind of see the same mapping. But again, this is like just for visual entertainment. Another part of this project that is conducted in collaboration with Shihab and Rupesh here, where is it? Yes, is looking at the response of ferrets. So the idea is that music enculturation is based on learning sequences that are, I think I'm almost done, learning sequences that are mostly pertaining to domain general auditory processing and learning. So we thought that we would be able to find similar results on ferrets. Very optimistic of us. But we took ferrets that were implemented in their with ECOG in their temporal lobes. And we looked at for 2 ferrets, and we actually have 4. So this is data, this is work in progress. But we looked at the difference, the activity induced by passive exposure, again, by looking at the ERP response difference between post-exposure and pre-exposure for these 2 ferrets. And we found that for the 2 ferrets test that we had, as opposed to the control, we found that we had activity difference around 200 milliseconds after onset, again, looking at these modeled ERP, which seems to suggest that these ferrets are indeed learning something about the statistical structure of the music they're exposed to. Finally, we know that there is a very interesting effect, which is called the wound effect, between musical pleasure and surprisal that goes like this. The more surprisal that there is, and the less surprisal that there is, less liking. And there is a sweet spot that corresponds to an intermediate level of surprisal. We also know that surprise-related activation is found in the nucleus accumbens, which is a deep structure of the brain that has to do with not only reward-related regions, but also learning, because it's dopamine, it's, how do you say, dopamine, sorry, I'm missing the word. Dopamine managed regions of the brain, or like this is where dopamine, those are dopaminergic neurons, I guess. And basically, we know that these types of regions are enhanced in the encoding of positive rewards that has to do with reinforcement learning for important survival features and behaviors, but also for neutral value features such as money and music. And that's what we see here. And here what we find is not only that, but also surprisal itself modulates the activity in these reward-related regions. So it's not just music in itself, but the more surprisal there is, the more activity you have here. And what I guess I'm saying with that is that we can now frame a whole sort of Neuro-Computational framework about the interaction between learning and pleasure in music that we can readily test with this whole framework that I outlined. So the idea is that you have a sensory response that comes back from I have to get faster. The sensory response is just the stimulus that enters the ears, and the prediction from this sensory response is modulated by the exposure, the long-term exposure of people, as we saw. And so basically, based on the difference between the actual note and the predicted note, we have a prediction error that's elicited, and we know it's elicited. Well, we don't know it's elicited from, but we know this response of prediction error activates the nucleus accumbens and these dopaminergic reward regions. So what we think is happening is that the pleasure of music is actually tightly coupled with also the learning of it. So when you have a music in which you are forced to update your model because you didn't make the right predictions, then this is when the pleasure is also elicited by means of this predicted error that's correlated with response in those reward regions of the brains. That makes sense? Which also kind of echoes with this example that I gave of the Schubert piece, where you have these expectations that are violated, but also seems to be immensely beautiful from a completely anecdotal point of view, but that's also important, right? So yeah, just to conclude, we can actually now think of the music predictability as a metastructural universal, because music differs in its way, the syntax, the way it's shaped and everything. But what might be universal is how the balance between complexity and predictability that you have. Because basically, if you look again at the surprisal and the cumulative corpus size, so how much you can approximate well the predictions based on how much you learn, you can have something that's too predictable, where you're going to be able to really achieve quite fast, very low surprisal, or too unpredictable because it's too complex, and so you can't really, be able to predict anything. And then you have this sweet spot that corresponds to something that's balanced in the terms of how music is structured, in the sense that it's a right balance between something that you can predict, but also something that is complex enough so that you can't approximate it perfectly. Which brings me to the idea that what's the name of this character? The bears and
Goldilocks.
yeah, okay. So this one, she had it right. She knew that the sweet spot was what was missing or what was important. There was future directions, and it's basically about how new types of models based on deep learning can inform the way we encode music. Very quickly, this is a transformer by Google Brain that was very efficient at producing Bach music. And surprisingly, it doesn't outperform idiom widely when we look at the cortical tracking of the surprise. But then there is another one that's called polyRNN, and I really don't know much about it, but this study found that it actually widely outperformed idiom. So this is something that we'll be seeing in the next years. And there is this study, which I find super cool, which is not looking at a decoder-only transformer, but an encoder-only type of transformer. So here you're not looking at predictions, but you're looking at representation embedded in layers of encoding. And Nima from Colombia looked at how the representation in the different layers correlated with neural response from people. And so first he found that the pitch class separability was higher for higher order layers of the model, but also that it correlated with better with EEG as you progress through the layers, especially for musicians. So yeah, thanks to all these people, this work was made possible.
All right. We're very fortunate to have with us today someone who's a bit of a rock star. So it's Professor Amanda Prorok from the University of Cambridge, who works in multi-agent and multi-robot systems. In the interest of time, I'll stop the introduction there and say, take it away, and thank you for joining us.
Hi, everybody. Thank you, Michael, for the very generous introduction. And I'm only sorry I can't be there in person. It's such a cool workshop, and I really am very grateful for the invitation I have to talk there today. First of all, hands up, everybody hear me okay? Yeah, cool, fantastic. That looks fantastic. Okay, cool. So I'm going to be talking about diversity today, diversity in robot behaviors. And as you see throughout my talk, I will be giving you a bit of a smooth introduction to some of the work we do that basically and hopefully will lead up to answering the question of why implementing diversity in robot behaviors is important and a really interesting research direction to be focusing on moving forwards. So just to give you a little bit of context to what we do in my lab, we are really driven by this idea that the next wave of computing is about agents that communicate and coordinate. And as you'll all be aware of, this is really nicely supported by tech developments to date, where we're seeing AI, comms, and mobile computing all kind of converging together and making these kinds of things a reality. And of course, we have been seeing how these things are a reality if we look to robot applications that are already being deployed in the real world. So those of you who are in the States will be familiar with Amazon and Kiva Robotics. Those who are back in the UK, where I am, will be familiar with systems like Ocado. And what they have in common is that they run really, really large-scale robot systems that have to coordinate at very high frequencies in pretty cluttered and slack-free environments. But we're seeing a lot of other really exciting things where like multi-agent systems are really starting to burgeon: precision agriculture, environmental monitoring, surveillance, cooperative transport for construction, and all sorts of things where we think that removing the human out of these systems would enhance our lives because they're either boring tasks, dull tasks, dangerous tasks, or dirty tasks. And then there's this other element, which I really like in my work too, and you'll see that in that little kind of image that I have on the bottom right, which is a picture of a swarm of birds. And I'm really, there's this other side of my work, which really looks into engineering multi-agent policies and behaviors, also because we want to understand nature better. And we're still in the process of, designing these robot behaviors when we're thinking about, well, I observe this macroscopic effect and I want to reverse engineer it to perhaps validate some assumption I have or some hypothesis I have about how the world works. And so this is kind of the scientific side of my work that kind of philosophically motivates me, and all the others are kind of from the application and engineering side where I think that we could put our technologies to use immediately. So how do I organize my research agenda according to all of this motivation? So I'm going to organize it according to these two axes here. So on the vertical axis, you see the ability of robots to be able to deal with less information. So those of you who are familiar with POM-DPs and market processes, so this is kind of the increasing ability to deal with highly partially observable systems where you don't know everything about the task that you have to do or the state of the world. And on the x-axis, we're looking at increasing complexity of the problem. This can be because I have more degrees of freedom, or it can be because all the agents in my system that I'm interacting with are different and heterogeneous, so not all the same, or simply because I have more of agents, more of the individuals that I'm interacting with, so the scale of the problem becomes larger. So it turns out that we already have really good solvers for systems that are either fully observable or relatively small in scale. And these solvers are either optimal or extremely good heuristics, but they really are excellent algorithms that have been applied to instances of these problems very successfully. But what we're missing is solutions to this regime that I'm calling online scalable. So really large problems that change a lot in real time, where we have to find solutions very quickly as a function of a new state of the world that are potentially very high dimensional, and where we have a global objective that we want all the agents or all the participants in the problem solving to kind of respect. Right? It could be, optimize throughput or do something, a very high level objective, and we want everybody to work together with respect to that global objective. And the problem here is that often these systems, they are deployed in the real world where we can't assume that we just have one kind of supervisor that is controlling everybody. So often these systems are at least partially decentralized, and they have to rely on local communication and local information dissemination schemes to function. And designing solutions for this is really incredibly hard. And that is why at my lab, just a few years ago, five or so years ago, we started focusing almost exclusively on solutions that embed machine learning components, either within or are completely end-to-end machine learned. And that's a little bit what I'm going to talk about today. So before I dive into the diversity thing, let me just tell you how we even begin thinking about engineering, like data-driven interaction between agents, right? And so we start with something very simple, which basically says that, okay, if I have two agents or two robots, I can model the relationship between these two robots with a function phi that essentially tells me how these two robots are interacting. So this function phi is an approximation of the interaction of these two robots. Now, if one robot wants to kind of pass information to the other robot, what this interaction feature Z tells me is it's basically going to say something about how robot J wants to influence the action of robot I on the other side, so downstream, right? And robot I is going to be ingesting this information that is coming in from another robot, and it's going to allow this information to influence how it's locally going to be making its decisions, okay? And so this function phi really sits in the middle of all of this and allows these two robots to somehow interact. And the beautiful thing about how we design the system is that we're going to make it scalable. So no matter how many robots are in the vicinity of a robot I, and I'll say something about what vicinity actually means to us in just a second, it will scale because my function phi is able to aggregate this information in a way that does not depend on the number of robots from whom I'm aggregating information from. So it might depend on it in a sense, you can sum them up, but it certainly won't depend on it in any exponential way, which is normally the problem that we have as we try to scale up systems. Okay. So now I have this kind of thing that I'm calling a collective context, which is what robot I is receiving. It's going to ingest this processed bit of information that says something about what all the other robots are seeing and thinking around it. And it's going to use this information to make the best possible local decision, right? This function phi is really quite magical because it can tell me what I should do as a function of, the state of the world and everything that my other robots are telling me about the world. For those of you who want to be a little bit mathy, this is kind of a bit of a deep dive into how we actually make this work and what the actual mathematical paradigm is that we use here. So we use something that is called a graph neural network. And what that essentially means is that we're kind of saying that the graph topology is our proxy for the interaction topology of the robots in my system. Okay? So if you imagine that my robots are nodes and the edges in my graph are the interactions between those robots, a graph. And then I can use this graph neural network to organize my data in such a way that training becomes really efficient because it's a perfect inductive bias to my system, right? And this equation that I've written down here, it turns out to be just one of the most kind of general ways that I can write it down, but we can become a little bit more specific in the case for graph convolutional neural networks. And what I then simply do is I say, well, my aggregation of information for my neighbors is simply a sum operator. And the way that topology is structured amongst my robots is going to be given by an adjacency matrix that can be time varying if you want, so no restrictions on that. And if I make those two assumptions, then basically what I see on the bottom right of this slide is how beautifully the whole thing pans out and is a simple matrix multiplication, right? Where the weights are right multiplying my feature matrix, and A here is my adjacency matrix. And it has an exponent K, which basically says how many hops of information I'm going to be considering. So it looks all really simple, and it really is, in this case, a very beautiful and simple paradigm. And the best thing about this whole thing is that even though the formulation that you see here is centralized, as long as every robot has a copy of W, so these weights, it's fully decentralizable, right? So incoming information can be aggregated locally on any robot in any whichever way that the information arrives. That information is basically populated inside my feature matrix that's right multiplied by my weights, which I trained a priori, and it spits out my embedding, which I then use in my next MLP, for example, for a downstream policy. So this is how everything kind of is strung together, and I have this policy that depends on observations that are made in my environment, and my function phi then basically gives me this context in my neighborhood. And what's really cool is, I didn't explicitly say this, but it doesn't only model interaction between agents, but once I have function phi, well, it is basically synthesizing the interaction. So function phi is responsible for what's being sent over Wi-Fi to my agents that are in my neighborhood, right? And so what I'm basically doing is I'm using phi to compress observations from what my neighborhood is doing to tell other robots in the environment how to interpret this potentially very large partially observable environment that I'm piecing together here. So what is one of the first things that we did when we started working on this? Well, we decided we wanted to solve one of the hardest standing problems in multi-agent research, which is the problem of multi-agent pathfinding. So this is a problem that is NP hard. In other words, it's one that becomes intractable as you scale the number of agents that have to do this kind of movement inside these cluttered environments. So for those of you who are not familiar with this problem, what I'm basically saying here is I have a whole bunch of agents. So for example, Amazon runs warehouses with thousands of robots. Here I'm showing you two examples with 40 robots. And it's a very difficult problem to solve because the agents, what they have to do is they go from locations, origins, to predefined labeled destinations. And they have to do this as quickly as possible without ending up in any deadlocks or live locks. And finding guarantees to this problem is actually really hard. So first principles algorithms for this are quite sophisticated. And on top of that, finding algorithms that do this with optimality guarantees is even harder. And so what we decided to do is, well, these optimal solvers, they don't scale. When you get to 40 robots, it takes 10 minutes to solve this problem. on an ordinary desktop, right? And that's assuming a static environment where nothing changes. So obviously, this is the thing that doesn't work without somehow leveraging, fancy tricks and heuristics. So we want to do better. We want to try and use a machine learning method that hopefully scales much, much better, but keeps some of the optimality, or at least empirically, keeps some of the optimality. And we achieved that. So we used this graph neural network, and we're actually one of the first to use a graph neural network to solve the multi-agent pathfinding algorithm. And so qualitatively, what you see going on here is on the right, our thing, which is running in constant time because every single agent is making its own decision locally. So there's no scale factor here. And on the left-hand side, you see a playback of a solution, which took, its full 10 minutes to be computed off board, right, offline. And so at this point, those of you who paid really good attention are like, well, did she now just solve an NP-hard problem in constant time? And kind of empirically, yes. But what we're missing is actually the guarantee. So definitely because our solutions are data-driven, we cannot provide the same nice, complete set of optimality and completeness guarantees that our standard solvers can, but empirically we're doing really, really well, both in terms of success rate as well as optimality, and more quantitative results are in the paper. So moving on from there, we had now reached this kind of level where we're like, okay, homogeneous systems work really well. I can solve really hard problems, but there is just so much more to solving really complicated problems in the real world. And what we really dug our heels into is this assumption that all the agents have to be running the same policy. So what does it actually mean that an agent has the same policy? Well, basically, what it means is that if you and I, if we make the same observation, you and I are going to take the same action, okay? So obviously, if you swap two robots in the workspace, they do different things. But if you then swap them again, they do the same different things, right? The policy is the constant here. And so homogeneity has a lot of advantages. It's extremely efficient to train systems that are the same because you only have one set of parameters that you're tuning. And they're very sample efficient because, especially if you're thinking of multi-agent systems that are very, large in scale, you can, the architectures, they do this thing which is called permutation equivariance, which basically means, the aggregation function that we use, the sum. It's a beautifully permutation equivariant aggregator because it doesn't pay, it's blind to the order of information which is incoming, right? So that's essentially what that means. Super sample efficient, and with a homogeneous policy, you can even emulate heterogeneity through things such as, we call it explicit indexing or inferred roles. So then at this point, you'd be asking yourselves, well, given all of this, why would we even want to consider heterogeneity, right? Where true heterogeneity, just a quick recap, what is that? It means that if you and I have the same observation, we're going to do different things, right? So if I'm standing in the corner of the room, I will go left. And if you, at some point in your life, are standing in the same corner of the room, you're going to go right, right? So it's almost, you can almost think of heterogeneity as a specialization, right? In the same situation, you're going to decide you're going to do something that's different from anybody else in your environment. So the problem with heterogeneity, although it seems like the more natural thing, right, that we have in the world, isn't really that interesting from a computational perspective because you can't do parameter sharing. Although you can do decentralized training, it's not efficient at all. You kind of have to construct some sort of centralized compute and aggregation of information. It's not permutation equivariant because the order suddenly matters. And you have a total explosion of the observation space because everybody is unique, right? So these are all red flags if you talk to people who do training, especially if you're thinking reinforcement learning, okay? So why would we even want to do this? And here's where I get into the meat of the talk. And I'm going to start with why. And to answer the question why, one of the best places to start is to think about, okay, how, like nature, why does nature have heterogeneity? And there's so many examples also from the human cognitive science perspective. And I just, cherry picked two here that I find kind of cool. On the left-hand side, we have ant colonies where we have heterogeneity that is also dictated by physical differences in the ant colonies. So these different ants, although they look different, they work really tightly together as one community. And what they figured out through evolution is that, well, if we evolve different body anatomies, we're also going to evolve specialized behaviors. So for the same observation, we're going to do different things. So the big ants are going to do guard nest they're going to do nest entrance guarding, and the small ants are going to focus a little bit more on grooming and a little bit of forage and maybe some feeding and stuff like that. And we see a similar kind of thing in bee colonies, although there it's a little bit less in terms of bodily anatomies, but more as the bees age throughout time. And what biologists uncovered is that as the bees age and they potentially become wiser, or maybe there are physical reasons that aren't immediately apparent, they start doing more of, say, patrolling and less of, say, cleaning cells. Okay? And so you have in nature all these examples of why organisms developed reasons to become different, yet to function really nicely as a team in order to survive and propagate their species. And then we can also look at engineering, where there are clearly a couple of examples where intuitively we look at them and we think, yeah, I think having a heterogeneous system here would actually make more sense than a homogeneous one. If we look at the left-hand side, I have a couple of examples of role specialization. So on the top, we have the passage scenario where we want one agent that just memorized, I'm going from left to right. Or in the passageway one, we have one agent that kind of memorized, I always have to go through the big gap. And I don't even have to know what size I am, because I just always learned that I have to go through the big gap. And that's the thing that will work for me, irrespective of how much noise there is in the environment. That's what I'm going to do. And then you can even look at games like football, where we know from the real world, different agents do different things, right? We have defenders, we have offensive players, and those players take in pre-specified positions in the game, and those pre-specified positions really play a role in the game strategy as a whole. And then there are even problems that fall into the NP-hard realm again, in terms of coordination, where having heterogeneous roles, so agents in the system. So here I have heterogeneity represented by color, and the robots, you can imagine that they're carrying different capabilities or sensor suites. They have to go and fill different sites with their capabilities. Solving this is actually a very hard coordination problem, and it turns out that having policies that are hard-coded into the agents as a function of who they are is much more effective than trying to figure out where they have to go if they're not running heterogeneous policies. So these are just a couple of examples from engineering world. And here, I don't actually know if the music is playing, but even if it doesn't matter, this is just a recent example from my lab where there, I have to stop because the music is blasting in my headphones, where we actually combined different controllers on ground as well as aerial robots to do a multi-agent pathfinding mission in 2.5D, essentially, where we're combining ground and air. So those are a couple of examples from the engineering world. So we decided to study heterogeneity. Our first deep dive would be in the area of pathfinding, because it's something really easy to benchmark and to measure our performance of, our first kind of results in the area. And we were really interested in pathfinding because it's, it looks so simple when you see things working, but actually what's under the hood is it's a very intricately difficult problem. Here's just an example of what I'm showing you above, and it's kind of there to emphasize how difficult it is when you actually decide to decouple the problem solving and allow every agent to think for itself. So if you look on the left-hand side and the agent is just thinking for itself and decides, oh, I'm going to move into my final spot, which is the green circled by the gray, then the blue agent will actually never reach its target. And that's what we call a deadlock situation. And that's actually why all optimal solvers are coupled solvers that operate in the joint state space of all the agents in the system. And that's actually why they're NP-hard, because as you increase the number of agents, your state space increases exponentially. But that's the only way you actually can guarantee deadlock freeness, because now the green and the blue agents are planning together in this joint state space. And if you deduce your solutions by searching through the graph that is operating on this really large state space, the green agent actually, its optimal move at the next time step is to stay put. And that's the only way that blue will actually move across and be able to reach its location, and then green will move across. And that's what these complete solvers do for us. What we decided to do is, okay, we're going to solve this problem, but we're going to solve it in a robot world, which is continuous. We're going to solve this in cluttered areas. And we actually want to do it with decentralized controllers, even though we think centralization is cool if you have it, you don't always have it. So we have to be able to fall back on local information dissemination schemes. And so we looked into the literature, and dug out the best current state-of-the-art algorithm that solves this for us in the continuous domain. Those controllers are called control Lyapunov and control barrier function based navigation algorithms. And what they do for us is basically ensure, that's the control Lyapunov side of things, convergence to goals. And they also ensure avoidance of collisions with other agents and also other obstacles. And that's the control barrier function side of things. Okay. And so if you put those two things together, you get all the guarantees that you need in the continuous domain. Right? There's a catch. You have to tune those systems because as for any robotic system, there's hyperparameters that say something about the physicality of the world. And before deploying these algorithms, you have to kind of set those hyperparameters to some fixed values. And we did an exhaustive search of all possible parameters in simulation before we deployed them. And then we deployed the system with the best parameters we could find. And lo and behold, this is what the system does for us. We want these 4 robots to go through this constricted passageway, and they're not able to do it. Okay. So we were super disappointed. We said, okay, so this state-of-the-art algorithm doesn't actually do what we want it to do. And so we had to take a closer look under the hood and figure out what was actually going on here. So just to give you a bit of an insight to what the math actually does for us here, it's from a dynamics perspective, it's actually really simple. It's just simple integrated dynamics with flow functions F and G that are basically just telling us how our robots are moving in the simplest possible form. And what we want to do here is we are at every time step, we're solving a quadratic program that generates my controls U that are basically this optimization problem is doing nothing else than trying to minimize my control effort, right? So if I minimize my control effort, I'm basically finding my most efficient path. And then come these 2 constraints that I've noted down here, subject to collision avoidance and convergence guarantees. Okay. You can just, lots of funny symbols there, but what you can think of them as here is just 2 potentials. One is an attractive potential, making sure that I actually converge to my goals. And the other one is a repulsive potential, making sure that as I get closer to an obstacle, I'm going to be repelled from it. Okay. And that's all that these 2 constraint equations tell me. So if this is the QP that I'm solving at every time step, why doesn't my system do what I think it's doing? Well, the reason is that the function that I have in my constraints depends on hyperparameters, and I have to tune those 2 hyperparameters, zeta and eta. Now, I can either be super conservative in the way I tune them, or I can be more aggressive. But either way, I'm either going to have inefficient trajectories. Like if I'm conservative, I'm going to make huge kind of detours around all my obstacles. Or if I'm too aggressive, the controls that I'm going to be telling my robot to execute might actually not be feasible and violate the plant dynamics. And so our idea was to say the following, and there are 2 key things here that were really our key insights. A, we're going to make those hyperparameters time varying. We're going to allow the robots to perceive their environment at every single time step, and they'll be talking to each other so that they can communicate what they individually know about the state of the world, so that they can somehow convey this information to all the other robots in the system, so that they can make the best possible decision of what these hyperparameters should actually be given the state of the world. And we're using the graph neural network that I introduced to you before as the computational paradigm in order to do this. And the second really important thing here is that, well, because every robot is thinking on its own and tuning these hyperparameters as a function of its locally perceived state and at every time step, the system is now actually heterogeneous. Okay? And so what that does for us is, you see in simulation here, the robots are actually converging to their goals. And on the right, you see how those hyperparameters are indeed varying throughout time. And as we now deploy this time-varying system onto the robots, they're now able to solve the problem and fit through the passageway. And what's really interesting is that what actually happened is that the allowing the robots to perceive each other and talk to each other and help each other make the best possible decision given this kind of common goal that they have, forced them to prioritize their passageway through this constriction. And it's really this prioritization that would not have happened otherwise with a homogeneous controller, because if you have homogeneity, then everybody wants the same thing. But with heterogeneity, you can be more like, yeah, you were a little ahead of me, so yeah, why don't you go first, kind of thing. And you're kind of taking different roles. One is saying, I'll go a little bit back so that you can kind of go more in the front, and we'll kind of do it that way. And that allows the robots to actually achieve the task. So heterogeneity really played a key thing here. What else does heterogeneity do for us? Well, I talked about specialization before. And we make this insight that specialization is super key when we take a solution that we train in simulation and then deploy it with the very same policy on the actual robots. Because what happens when you take a policy from simulation and you pop it onto a real robot in the real world, well, you don't have the same noise. You don't have the same conditions. No matter how hard you try, simulation will always be a bit different. In our case, observations are different of each of the robots, seeing each other. There's friction on the floor that we don't simulate properly in simulation. And that creates those teeny tiny little differences that actually make the whole difference when the policy executes. So in this case here, if we take a heterogeneous paradigm where each robot is learning its own little brain and its own little policy of how to do this kind of swap task, it seems to work really well as we transfer the policies onto the real world. If we have a homogeneous system and we force both robots to have the same brain, and we then take that policy and redeploy it onto the real system, what happens is actually really interesting. The robots get to the midpoint of this crossover task, and they start getting really confused about what they have to do. They kind of start hesitating and kind of going back and forth. And the reason they're doing this is because the observations aren't crystal clear anymore, not as clear as they were when they were trained in simulation. And the fact that there's just ever so slightly this amount of noise in this very critical moment when they have to do the crossover task makes them hesitate. Well, am I the one that now has to go left or right? But we didn't have this issue with heterogeneity because in that case, the robots are specialized. One robot specialized, he's always going first to the left and then to the right, and the other robot specialized, he's going to do the opposite. So here, heterogeneity and role specialization just makes you super robust at what the world is actually going to be throwing at you, because no matter what the state of the world is, you just know what you're going to do. And we found that really practical for robust coordination with robots as you transfer policies into scenarios that aren't completely as expected. So now that I've hopefully motivated why we think heterogeneity is so interesting, I'm going to show you the two tools. I'm going to talk about the two tools we need in order to make heterogeneity actually happen in such a way that it's useful to us. And the first tool I need to talk about is, well, before trying to control diversity or do anything kind of more targeted with it, I simply have to be able to measure it. Okay. And so what I did together with my PhD student who led this work, Matteo Bettini, is we devised this metric, which we call system neural diversity, that says something, given a set of policies in a multi-agent system, it tells me something about how different these policies are. So in this particular equation, it's actually really simple. It's nothing else than the average behavioral distance between every unique pair of agents in my multi-agent system. And it's a very nice property because it satisfies all the official properties of a proper distance metric. So it's non-negative, it satisfies the identity of indiscernibles, it's symmetric, and also satisfies the triangle inequality. The one thing that we had to implement here is a way of actually measuring dij, which is the distance between two robot policies. Now, if you'll remember, our policies, they're actually distributions, they're action distributions. So you can think of them as unimodal Gaussians with a mean parameter and a standard deviation. And so we actually need a distributional way of measuring the distance between these two policies. And so there are a variety of different ways that you can measure distance between distributions. Many of you will be familiar with Kullback-Leibler. And we went through all of them, and we decided that the Wasserstein distance is actually the best one for our cause. The paper goes into a lot more detail with respect to why this is the right metric. And so taking the Wasserstein distance and our two policies for every two unique pairs of agents in our system, given any possible observation that the agents can make in our system, we now have a closed form equation that is able to evaluate the diversity of my multi-agent system. And now you're thinking, okay, but actually my observation space is not integratable in a continuous manner. So how do we actually in practice do this? Well, the integral, we simply replace it with a Monte Carlo sampling of the observation space as we execute the policies in our actual environment via policy rollouts in these given environments where the tasks reside. So this is our SND. And now what can we actually do with it? And is there anything interesting that we uncover with it before we even get to the controlling part? And so the answer to that was actually yes. And it was really surprising and at the same time really exciting. So we came up with this task where we had two agents that don't actually observe anatomical differences, that they're actually physically different. And what these two agents have to do is basically they're rewarded for the amount of wind, the inverse amount of wind that they actually feel. So they're kind of like exerted to this wind coming in from the front, and they actually have to fly like it's some sort of formation, either next to each other or behind each other, and deflect the most amount of wind possible. So it turns out that this triangular agent deflects wind and the circular one doesn't. So the best possible configuration as a function of how we've defined the reward is that the circular agent flies behind the triangular one. And the thing here is, the catch is that they don't actually perceive their anatomical differences. The only thing that they will perceive during training is that the reward is higher when the blue one is behind the triangular one. And so if you look at training, when the wind starts, both policies, both the heterogeneous one and the homogeneous one, they start to perform better. Obviously, they learn how to deflect the wind, but the heterogeneous one is much more performant because it is able to learn the specialization that when the wind starts or when there is wind, the triangular agent will always be in front, and not only 50% of the time. It'll always be in front because that's the specialization that the triangular agent has learned, in which it receives the biggest reward. If we turn the wind off, both homogeneous and heterogeneous controllers perform the same. And if we turn the wind on again, you see that there's this difference again between homogeneous and heterogeneous controllers. But now the important thing in the plot that I want you to see and to perceive is that there is 0 ramp-up time for the heterogeneous controller to reach this high-performing, performance level. And that is really interesting because this is training curve. This is not inference, this is training. And so we looked into the SND, so the metric that we developed, to understand whether that would give us any insight as to why we have immediate benefits of why heterogeneity gives us this immediate benefit. And basically the answer is that, well, our system has memorized that being diverse is interesting. And so even when the wind has stopped and disappeared completely, and the system is still learning, you can tell how the diversity is starting to drop slowly, but it doesn't drop abruptly. So the two agents still remember that they specialized for some really important reason. And the specialization is retained. And so when I turn the disruption on again, the two agents immediately remember, oh yeah, I was the one on the top and I was the one at the bottom, and they can retain those, they can reposition themselves in that way. And so this period within which there is no disruption, but I'm still behaviorally diverse, we call it this period where we have latent resilience built into the system. It's not needed, but it's there in case a disruption would happen. And I would argue that we see this in nature quite a bit. So natural communities, they are diverse because you never know what nature is going to hit you with. Maybe it's going to be a hurricane, maybe it's going to be a wildfire, and there will be certain species that have the necessary skills to deal with that, and that will allow the community to survive. And we think that we've uncovered something really similar here with our S&D measure. So these latent skills allow us to be resilient. And so we can do a similar kind of example with a gap that narrows abruptly, and we have exactly the same type of plot where we see and uncover this latent resilience that we found was really so interesting in the system. And so I'm now coming to the final bit of my talk, which is, okay, we developed this S&T metric that allows us to measure diversity. What can we actually do with this measure, apart from saying, oh, we've uncovered latent resilience? Can we actually control diversity, and how would we do that, and to what end? Yeah, take a sip of water here. So we came up with this idea that if we control diversity, it can be really useful for given tasks. Let me explain to you first how we actually think about this. So we came up with this algorithm that we call DECO, short for diversity control, where we basically are telling the agents that they have a certain amount of diversity, so a diversity budget, that they can spread over the observation space, right? So what this essentially means is that if you and I, we have the same observation. So if you think about this plot here that I'm showing you visually, say my observation space is 2-dimensional. In this 2-dimensional plane, you and I, we can be different by X at position Y, and Y is a two-dimensional kind of coordinate in this plane. And so what you can see in this cartoon is, yellow would mean that we're very different for that given observation in this two-dimensional plane, and blue would mean that we're actually similar. So if we're in the blue space, if the red and the blue agents are in the blue zone, they're more likely to take a very similar action if they're in that position in the observation space. And so the other interesting thing that we did was we thought a lot about how to make our diversity control architecture more effective with respect to this parameter or sample inefficiency that I mentioned to you previously. And the way we thought about this was actually to say, well, how much of the policy or how much of the network actually has to be really different? And can we only just do a couple of the layers at the end that actually have to be different, and everything else can actually be shared? Isn't that enough? And so that's exactly what we're doing when we actually implement this practically in our multi-agent system. We actually have a component of our network or a component of the policy that is shared. And then we have per agent deviations that represent from this shared amount, from this shared kind of component that everybody knows how to do the same way, there will be deviations. And it turns out that this formal representation, as well as the practical implementation of this formal representation, is much more efficient than making policies completely heterogeneous. And so the practicality of this leads to the proof that we are actually able to maintain and to guarantee an exact S&D value, a desired set point for my controller that is trying to learn diverse policies at every given training time step as I train my robots to be different. Okay? And I do this, here are a couple of technicalities, but I do this by first scaling and normalizing all my robot policies, and then making sure that the deviations, when summed up, result in precisely the set value that I'm setting my robots to, which is given by the S&D, the desired S&D that the user has told the system that it has to reach. Okay. So if I implement my learning algorithm in this way, I am guaranteed that all my agents at every single learning step will have exactly the desired diversity. And what does this actually look like for different diversity values? So you can see at the very right-hand side, I have unconstrained diversity, and you can see the blue and the yellow are kind of a little bit random in the space. And on the very left-hand side, everything is blue because I have no diversity, so the two agents take the same actions. And what's interesting is the two plots in the middle, and they make a lot of sense if you actually introspect them a little bit, because in this task, what the two agents want to do is they actually want to reach their predefined goal positions, right? So red wants to go to red and blue wants to go to blue. So if they are coming at it from, like, say, from this angle, right? Then red and blue both kind of have to move down the arena into the same position until blue kind of continues. But those two motions are the same. And that's why that zone is blue, because for that observation, the two robots are taking the same action, right? But when the two agents are in between the two goals, right? So red has to go here and blue has to go there. That's when their actions are diametrically opposite. And that's when the policies are the most diverse that they're ever going to be. Right? And that's why we have yellow there. So if we have controlled diversity and a set diversity budget that we can distribute over the whole observation space, the algorithm learns to give the agents the diversity in the positions of the observation manifold where it's most useful. And that's what's so key with this algorithm. It distributes the diversity there where it makes most sense. So what can we do with diversity control? Well, we can now solve tasks much more effectively. So if I think of all these little games that I'm showing you here, for example, field sampling, where the agents have to distribute fast and sample an environment, you're much faster and effective if you have diversity, because as you can see on the right-hand side, they specialize in different areas of the environment. Dispersion as well, they reach to different goals much quicker. And on the very right-hand side, you see two games where the green agent is going to get tagged by the red agents. And the two red agents are learning complementary strategies. So one is kind of doing the ambush thing, whilst the other one then kind of swoops in. And then the other one, we're doing a cornering maneuver, where the other one kind of is watching how the green, the agent that's trying to get away, watches how it's going to try to get away and then kind of swoops in as well. So highly complementary strategies that work well together, but they're different, right? These two red agents, they learn different strategies. So this could not have been done with homogeneous controllers. And so this was really cool insight that was purely emergent through the fact that we were forcing the various agents that were being trained here to be different. And so the very last thing that I'm going to now show you as I close off my talk is this example here. So we decided we would tackle football in a scenario where, so the blue agents are the ones that we're training, and the red team is basically just a team with some heuristic algorithm that we trained by hand, that we wrote up through by hand. And we told the blue agents basically nothing. We told them, you don't know how football works, apart from the fact that when you score a goal, you get a +1, and when you receive a goal, you get a -1. But we didn't tell them about, all these human biases, such as offender, defender, and all those different roles that you could have. So we wanted the system to figure out by itself what would be the best possible strategy it could learn if the blue agents were forced to be a little bit diverse, right? And so this is what happened. So this was at the end of one of our training runs, and you could see how we have this emergence of very clearly defined roles in our blue system. So one of the blue agents decided it would be the goalkeeper. Two of them are kind of hanging out in midfield and are took on defender roles. And two of the other ones are kind of like hanging out in the front, which clearly means they're in the offense. And if I show you more of these playouts, you can see how all these different role instantiations really came to life through this diversity control paradigm. And in our paper and archive, we were able to show that diverse controllers were always able, when we kind of baffled them against homogeneous controllers, able to outperform the homogeneous counterpart. So diversity not only had a role here, but also the fact that we controlled the diversity here also came up with the exact roles that we humans intuitively thought of as being the right roles. And that's how we design our whole game of football, right? With offense, defense, and goalkeepers. And we really found that phenomenal because in our case, it was 100% emergent without any prior constructed biases from our hand. Okay, so this brings me kind of to the close, and I just want to acknowledge that this kind of research that we do is only possible due to the development of a lot of tools. So we develop libraries for multi-agent reinforcement learning. We develop simulators so that we can actually prototype our policies very quickly. And we also develop our own robot platforms, sometimes using off-the-shelf components, but sometimes built very much from scratch. And I really want to acknowledge my team who put a lot of effort and work into developing the tools for the research that then ultimately leads to the interesting results. With that, just a couple of things. So where is this whole research around diversity heading next? So we're really thinking about, we saw that diversity is great, and we saw that we're able to control it to given set points to really interesting effect and impact, but we don't yet know how to optimally set the heterogeneity levels apart from doing exhaustive search. And another thing that we're really interested in understanding is, well, in which environments do heterogeneous controllers really thrive? And when is it maybe better, after all, to use homogeneous controllers? So we're looking into that as well. With that, I'd just like to thank all of my team and my sponsors and all of you in the audience today for paying attention to me so early in the morning. Thank you. I'm happy to take more questions now.
Just before we dig into the questions, our speaker has a hard out at 5 minutes past the hour. But yeah. Amanda generously joined the WhatsApp, and so interaction there is also a possibility. So. Yeah, Jason.
Hi, Amanda. Can you hear if I'm speaking?
Yes.
Can you say a little bit about the scale up of putting the heterogeneity on many more agents?
Mm-hmm. Yeah. So it's challenging because if you want heterogeneity, it means that you need at least some of the parameters to be unique on every agent. And so we actually, in many cases, we do centralized training. That's not deployment, that's at train time. And when you do centralized training, you have some, like, if you remember from my slide, this weight matrix W, that's then going to be, you need one of them for every agent, right? So it won't scale, say, exponentially in terms of memory, but it will do exponentially as a function of the observation space. And that is something to be aware of, especially for very complicated coordination tasks. There are definitely ways that you can make this whole thing much more efficient. And there have been 1 or 2 research papers pop up recently, and we're also working on that a little bit. You can, leverage things like hyper networks and architectures that kind of help you with that. So it's not an impossibility to kind of try to maintain efficiency as you go down the heterogeneity route, but it just takes a little bit more work than if you would go with the vanilla homogeneous counterpart.
Thank you.
Yeah, thanks for showing that stuff. Could you explain, like, in concrete terms, how big are the neural networks that are being used here? Like, what are the inputs and outputs of the networks, and how are they being trained? In one of these examples, for example, really simple one.
I mean, it can be anything from a very small and like 2-layer MLP type system. I mean, the problem is it really depends on the task. So football is going to be the most complicated one, where I don't remember offhand the size, but it's going to be larger than, say, the passageway scenario, where we're literally looking at an input space of maybe, I don't know what we had. It's less than a dozen dimensions at inputs, and the output is typically velocity. If it's in the continuous domain, it might be a little bit more. If it's in the discrete domain, it might be, depending if you have the stop action, it might be something between 4 to 6 elements in your output vector. So
Okay,
quite small, but it can be anything in between. Yeah.
Okay, so the input is like some measure of what the neighbors are doing and what the goal is, and the output is the direct control, like the desired velocity of the robot. Is that correct? Or the input is this graph structure, right?
So it depends if your question is it the input at which part of, like, because my neural network has multiple stages. So I have the observation processing bit, and at some point you get the input to the GNN bit, which is the communication part. And then you have the output of the GNN part, and then you have the input to your, like, say, action policy at the end, and then you have an output of your action policy, which is just your, like, actuators, for example. So there are many different stages in there. Normally, it depends on, again, what you're doing, but if you have vision as your input, you're going to start with a very, very large input in terms of vision. Like, it could be your 320 by, I don't know, 124 pixel that you kind of concatenate. So you have very large input at the beginning. But the goal is that the embedding that you send over wireless is typically no more than, say, 124 or so values in your embedding. But again, it depends, because if you're wireless and you just have, like, if you're wireless, you're not going to be able to manage like tight control loops, because it gets clogged up really quickly, even with just 124 elements in your embedding space.
Okay,
so there are a lot of delicate design decisions that have to be made here.
Okay, so in terms of the workshop, if people wanted to play with toy examples to explore this kind of work, because I think everybody would be in kindergarten completely, it would be useful if you could put a link to the simplest possible toolbox that would allow people to play with this. Do you have from your slide with your tools?
So VMAS.
Can you show us the webpage for that?
Absolutely. Let me just go back to this. So you can actually just take a picture of the GitHub and you'll get everything there. Let me just share that again.
So yeah, I had the question too, is it all supervised trained? Do you have supervision for the training?
Oh, right. So the training paradigm is
planning algorithms.
Share. So if you can, like, this is the VMAS simulator. We have the QR code for the GitHub. You can take a snapshot of that. And that is actually really great to get started with some of the things that we do. It's a really good stepping stone. It's very didactic. I'm more than happy to share that also over the WhatsApp channel. I can post that again afterwards. So the question was, how do we train? And the answer is you can train using any paradigm. And we've done all of it. We've done it with reinforcement learning. We've done it with imitation learning, and we've done it with supervised learning. So any training paradigm works. Most of the things I showed you today were trained with reinforcement learning, but you could, the multi-agent pathfinding thing that I showed you was actually done with imitation learning, where for very simple problems, we just recorded the optimal policies actions. And then we trained a policy to just copy that in small sizes, right? And then the key is once you can do that on very small size instances, the same thing, the same policies can then be executed on very large sized instances. So generalization is really key here.
Thank you.
Yeah.
We have 2 minutes left, so I think maybe we should, for safety's sake, call it here.
Yeah.
And again, for speaking.
Thank you so much, everybody, and more than happy to interact over email or on the WhatsApp.
So let's start with Misha's silicon retina, right, which is this passenger circuit. So you have a photodetector, and then you have a load of 2 PMOSes. For now, we ignore the fact there are 2 of them, but basically a diode-connected transistor, right, will perform. So a transistor, again, let me just go back to what I said, right? So transistor is a exponential element that gives you a current that is exponentially in voltage, in gate voltage. So if you turn it around, if you do feedback, so if you connect the gate to the drain, get feedback, they turn it around. So then a current gets converted to a voltage that is logarithmic, right? And so you get a log encoding here of intensity. The follower here basically means that just gives you it buffers that weak voltage into a lower impedance output. And then you have this network. We call that, so what Andres call this diffuser. So we call them.
That transistor is a current source, it goes into the 2 diode connected transistor.
Yeah, it's also current, yes.
That's how you get the log encoding.
Yeah, so it's indeed.
Nothing to do with the transistor.
Well, there's a log encoding here, right? There's a log encoding here.
Exactly. That's a log encoding.
There's a log encoding here, and then here's just actually the transconductance amplifier into this network of laterally coupled conductances, right? And that does diffusion. It gives you a spatial average of your intensity, and then comparing that spatial average with the actual intensity here gives you spatial contrast. So that's basically the premise. And it worked beautifully with fixed pattern noise aside, right? You can see here the Misha's cat, and right, you can notice that on average everything is I guess mid-level because this spatial high pass filtering will remove any DC component that you have in intensity. And what you have is then just what you get are the high pass filtered versions of the image, which is basically your edges, right? Your edges is what you show here. So that's the concept of spatial encoding. And then here, you can combine that with temporal encoding too. In addition to this horizontal cells, bipolar cells giving you that spatial contrast. You can also have this amacrine cells here to give you temporal contrast too. So that brings us to the precursor of the DVS sensor, the dynamic vision sensor. This was work. This started that's at Johns Hopkins with Rav at Cummings. In fact, we had Say again?
You showed these slides before, right?
This one, did I show this one?
Yeah, you showed all
I showed this one. Okay, fine, I can go. But I do want to talk about the circuit though. Okay, so let's go over the circuit, and maybe I should zoom in and go. Okay, so first of all, what you have is on the left is a standard APS sensor. APS stands for active pixel sensor. And a coupling to that, capacitively coupling the output of this APS sensor to a detector, in this case, a distributed comparator, will allow us to do basically comparing the intensity against a stored value that is stored across this capacitor that encodes history. This way you can do then temporal differencing as opposed to spatial differencing. And anything with charge domain works much easier doing temporal differencing or spatial differencing just by the fact that with temporal differencing, you get advantages of something that's called correlated double sampling, in that you can effectively taking a difference between 2 measurements. You take a measurement at one time step, and then take a difference with a measurement at a different time step. And any offsets that you have in the circuit will be canceled out. let me actually go a few minutes over that to explain this. Right? You can go on the whiteboard for that. Maybe I can stop sharing for a moment so you can see the whiteboard. I guess so. Yes, you should get it. Okay, so here we have a your active pixel sensor is basically a photodiode that produces a current that is proportional to the amount of light that comes in. Right. What we had in Misha's pixel. Well, first of all, this was a bipolar transistor. It's just a little detail. We had a diode-connected transistor up there. Let's replace this now just with just a single transistor. And in fact, that turns out to be as good as almost anything else, right? So you can just have a constant gate voltage here on this NMOS transistor. And then the source voltage that you have of this resistor will give you a log-encoded version, right, of the intensity. That's for continuous time measurement. But you can decide to do different things with this node here. So rather than having a constant voltage on the gate, you can also just use this as a switch in which you can do a reset. You can reset the voltage on this output node here at time 0, beginning of a frame. And so this can be then just a reset.
So the advantage of using the N is also another one. You don't have the kappa, also you don't have one on.
Yeah, there's so many advantages. But so now we're getting in the charge domain, because in addition of this circuit here, right, you can just look at currents, continuous time currents flowing. You can also think of this node as a capacitor. There's intrinsically capacitance there. You can add some capacitance if you want to, but you're better off not even adding anything, because the parasitic capacitance is good enough for all practical purposes. So you can just charge up a capacitor. In fact, charge down the capacitor. So you reset the charge. Let's say here, you reset the charge across this, right? You at time 0 when you do reset, right? You reset. The voltage here, V photo, would be at VDD or close to VDD, right? So V photo. And then the voltage will decrease according to the current flows, right? So this is right. For capacitors, you have right. So I over C is the slope. So I photo over C of that node, right, gives you the rate at which the voltage decays. I guess you can put the minus sign here. And so then the trick in an APS sensor, an active pixel sensor, as a frame-based system, right, is right. So you, at the beginning of the frame, you reset the pixel, then you let it go over the entire frame, and so you can actually serve different rows in your imager while this integration takes place, right? So when you say frame, this can be a rolling shutter, where the voltage now decreases, right? And by the time you circle around in your query-driven fashion, right, and you return back to this row, now you can read out the voltage, right? You can read out this voltage. So this is after frame, right? And so, of course, the voltage you get now is going to be the difference between the voltage that you measure now and the voltage that was before is proportional to how much light came in, right? Now, a strict correlated double sampling technique will cancel out the buffer's offset, right? And where's the buffer here? Let me actually make this concrete. In the case of an active pixel sensor, the buffer is simply the source follower, right? You can even have it addressed, right? So in this case, the source follower, that is a select line. right? And then on the output, you can just read it out. So at the periphery of your array of cells, you can have a current source here, right? And the voltage that you measure, here, the output at the periphery of the array is then a followed version of the voltage you have up here. Just quickly for those that are not too familiar with this mixing of circuits, right? So whenever you have a source follower is basically a common, we call that a common drain. What is it?
Common source.
Common source. Common drain, right?
Common drain, yes.
The drain is common. The drain is VDD. The input is in the gate, and the output is in the source, right? And so if you fix the current that goes through it, then the gate or source voltage must be approximately constant, which means the output and the source that is transferred here, right? When this row is selected, will be a constant difference away from what comes in here. But a constant difference, you don't know what it is because it depends on the threshold of the transistor, it depends on many factors, right? You don't know what this threshold is. But you're okay if you do the measurement 2 times, right? You do the measurement here at the beginning of the frame, right? And you get whatever offset you get, right? And you do the measurement again now at the end of the frame. Taking the difference between these two will cancel out that offset. And that principle is called qDVS, which stands for correlated double sampling. Now, strictly speaking, that's not all we can do here because we can't afford to remember all the, right? Have a memory somewhere where we store all the values for all the rows. At the time when you hit this particular row, all you can do is, rather than approximating whatever offset that you have here at time 0, right, when you sample to VD, you can turn it around, and rather than taking the difference between now and the previous frame, you can do the opposite. So now you take a difference between what you measure now, and then after you do the reset now again, because you have to, after you've done this measurement, you have to reset the pixel anyway for the next frame, right? So we have another reset pulse here. And that brings us back up to VDD, right? And so what to do is now this differential measurement, right? We first measure the signal, and then we measure what the reference would have been in case, right? What the pixel does for reset is exactly the same as what it did a frame ago. Is it a good assumption? Yes and no, because there's charge injection noise, there is variations, right? But for all practical purposes, this is okay. Right? It's not called CDS. What is it actually called?
DDS.
Double, right? DDS, right?
Differential double set.
Yes, DDS, whatever it's called. Yes, yeah. Okay. So that's an APS. So you're nothing because this has been around Eric Fossen, right, for 20 or 30 years now. But now it gets interesting.
Also, that's a linear, which you know now, this is a linear pixel.
Yeah,
But I
it's a
have to
linear,
say,
yes.
This is an APS pixel circa 1990.
Yeah, exactly. Yeah, 30 years old.
Part of that pixel.
Yes, and now, how does it become interesting to us? So how we can now extend this scheme for rather than just outputting intensity, which is fine if you care about frame-based intensity, because in this community, I don't have to preach and say that, no, we don't want frames, we want events, right? So how do you turn this into event-driven sensor? So what we realized, this was also 20 years ago, 2000, early 2000s.
The original paper you have.
Yeah,
Sure.
yes, this was ICC. In fact, this was
Nice.
ICC a
Nice
year
paper.
before the DVS ICC paper.
Nice paper.
The problem with your scheme, what you're going to describe
Yeah.
now, is that it.
Yeah.
Okay, got
It's
it.
not event driven. I totally
It's the
agree.
reason that it was abandoned.
What's the reason?
Well, I'll get one. One second. Okay, so this is right. So that's good. Now, in fact, what we did let's go back here, share. What we did here Yeah, we directly take the same node for the APS. So you can get a node APS readout. But then we get some other circuits around here. And now let me focus on the additional circuits that do basically differential computation. And then, as Toby already alluded to, that itself is not too great because it doesn't give us an event output. But then with Rauch, right, a few years ago, or no, 6 years ago, right, we actually did a version of this that is truly event-driven. Although it still requires a query, but this query can also be asynchronous. So I think we can close the loop on exactly what you were suggesting, Toby, right? So we can do actually asynchronous event-driven imagers, but they're actually query-driven as opposed to purely event-driven. So, and the reason why
By query, it means that they are synchronous.
yes,
By demand, on demand.
yes. In fact, let me go over this because I didn't go over that, right? So you have active pixel sensors. I just talked about that. That's what we have here. Then we have event-driven dynamic vision sensors. This is basically a Lichtenberg.
Probably.
Yes, this was a
Yes.
and then we have the query-driven versions, right? So, and in a way, the query-driven version is somewhere between the event-driven dynamic vision sensor and an active pixel sensor, in that you still have a row multiplexing of activity, but rather than outputting, buffering the analog output with a cost, right, of a lot of power, because there's a bit of noise. We just output events. So we do a temporal differencing right at the pixel level, right? And of course, there's a trade-off here because this means you can only detect events or changes as often as you can circle around, right?
That frame rate.
At this frame rate, yes. And so with Raj, we'll see where we accomplish this to be kilo frames per second. So basically a sub-millisecond times to go around, even with 128, right? 256, yes, 256, yeah, 256 rows. So you've got a 256 by 256 pixel imager that is event-driven. But yes, you can detect anything that's faster, say, than a millisecond, right? So there's a trade-off. But the advantage here is that you don't have to burn all this power constantly waiting for an event to happen, right? Because here, yes, this is, if you want microsecond speed in detecting events, you have to drive those competitors, everything, right? At enough juice, enough power, so this is constantly on. And so you can have one event that happens every second, but then the entire you keep going this needed, right? To drive. And I hear someone over the internet, over Zoom.
No, it's just something.
Okay, yes. Okay, I guess so the premise here is to let's see if we can have this hybrid, and we pay a price as far as speed at which we can operate. Although now we can make all this scheme also asynchronous, we can actually speed things. We can make the system go as fast as it can. The scanning can happen as fast as you can. There's no need for any clock, by the way, right? There was need for a clock in
Are you reading out pulses or
Location.
just location? I see.
pulses, yes. Yeah, so here in this case, so I'll just continue here, right?
Did you make one with a comparator at the edge, Brett?
So yeah, so
Yeah.
here the comparator is in the periphery, the
Right,
corner.
yes.
So we try to reuse the comparator every time there's a row select. That's when the comparison happens.
Yes.
We only need to do comparisons per row,
The row.
not in every pixel.
Right,
So we make the pixel compact.
Yes,
lower
yes.
power.
and you put Perot, yes. And I think where that paper, this is the next paper that is not there.
No, it's there.
Yeah, this one is in the CICC. 2021.
Yeah, this one here.
Okay,
Let me actually walk through this.
that's a
Right?
very nice paper.
Yeah. Well, let me just start from this, right? Because, okay, so here you have your follower, and then, okay, let me probably stop sharing here. And now you have a comparator. Now, what is a great way of making you can make a dynamic comparator if you have a truly synchronous system, but let's walk away from that because I think we still like to have an asynchronous interface, right? So here's a very simple way of implementing a correlated double sampling comparator, basically for measuring a temporal difference, right, between current intensity and previously registered intensity, right? So you have you capacitively couple. I'm not sure you can see this, right?
Yeah, we can.
You capacitively couple the output, right? And I just draw this as an inverter now, but so the inverter we can distribute it, and the nice thing is we can only have the NMOS part of the inverter that is in the pixel, and anything PMOS and any other codes can be out of the pixel, which means the entire pixel has no end well for this, right? Because end wells are expensive, they occupy a lot of area. And so everything inside the pixel can still be NMOS.
Yeah, but there's a different layer, so it doesn't matter.
Yes. Yeah. Well, yeah, no, you cannot recycle the end well for the diode as a VDD. That'll be short. You can do it, right? Yeah. But yeah, so in principle, let me actually simplify it. Right? This is a very simplified picture, right, of how you can do a temporal differencing, right? How would this work, right? So that when you close the switch, right, so we can synchronize with the reset that happens here, right? You will establish the inverting point of the amplifier, whatever it is. Let's call it 0, but if it's not 0, who cares? Because the current double sampling will actually remove that offset anyway. Whatever offset, let's call it 0 for now, right? There's a 0 up here. And of course, here you have the intensity that you care about now. Right? And then you open the switch, and a moment later, now you measure, right? So basically what we have done by closing the switch, we have memorized across this capacitor the voltage that you had on the left, right? And then now, right, so that's go to this framework, and actually probably should stop. Again. So in this case, now you have this V photo that comes out. So next time around, right? Let's say next time around, I should draw this again here, right? So you will have this one, maybe next time around. You may have more intensity, which means you would have gone deeper, right? So here, this is the intensity that you had at the previous frame. Here's the intensity that you have at the current frame. So what you did is across the capacitor here, right? You have stored, effectively, you have memorized the voltage up here, such that at this time up here, at the next time, when you do the comparison against 0, right, with the switch being open, right, your output will now be high if this voltage were lower, and the output will be low if this voltage were, right, higher, right? A very simply inverting comparator. And the nice thing is this circuit does it normally. For a comparator, you need to have 2 terminals, right? A normal comparator is this, right? You have a plus and a minus, and we could have done that, but this is much bigger, first of all. Second of all, this is prone to mismatch, because then you're stuck with the mismatch between, right, of the amplifier, of this comparator, right?
The diff pair.
The diff pair, differential pair, yes, yeah. So in this case, for temporal differencing, this will give you an almost perfect temporal difference, no matter what the offset of this, right, or the inverting point of this amplifier is. Right? So that's the main premise here.
Also, you get, because you're using an inverter, you get twice the gain of the compared to a diff amp, because on a diff amp you get half, and by using the inverter there, you get A is twice as big as the gain of the diff amp. So everything works better because your negative feedback now is better and whatnot. You
can even give it greater gain if you can have a fully complementary one with, but that we can't afford to have that because
you control the threshold.
You don't need to.
No, but how about if you want to increase the threshold to reduce the event rate? Does this all have a very tiny threshold?
Oh no, yeah. This still has a bias, right? No, yeah. This still has a bias, and the bias is given by the circuit in the periphery.
But that bias doesn't adjust the gain of the amplifier. At least if that amplifier is running in subthreshold, the voltage gain will be fixed by the transistor.
GM over GD.
Yes, exactly. Yes.
We have 2 GM over GD. 2 GM over GD.
Yeah, the gain of the amplifier is the
same. Fixed voltage, fixed high voltage gain, right? So you can't,
hold on. So
you can't increase the threshold to reduce the event rate.
But you can. No, well,
Toby, do you want to add an extra capacitor to inject a threshold charge?
No, well, yeah, we get to it. Yes, of course. Christopher knows what I'm talking about. Yes.
And the other thing is you'll get to the switch charge injection later, right?
Yes. Well, fine. But let's keep going.
Let's keep going.
Yeah.
Yes.
Okay. So far this circuit, this is not what we do, because all it does is compares against the previous one, right? So in this case, your threshold would be the previous value. So right, if you're below the previous value, your output will be high. If you're above the previous value, your output will be low, right? Now, what we'd like to do in event-driven imager, we would like to have this plus or minus epsilon, right, of a change. We just don't want we're not just interested in knowing did the intensity go up or down. We want to know, has the intensity gone up by at least epsilon, or has it gone down by at least minus epsilon, right? And we can define this rubber band, this right? And this is now, the trick here is we do this by just adding one more capacitor here, right? So we add one more coupling capacitor. And the beauty of charge domain circuits, everything's beautifully linear in a charge domain. You can just have, and so don't get fooled when people are very excited about switch cap circuits, because switch cap circuits are the worst things to do. Yes. You don't want to use switch cap circuits in imagers or in computer memory, because they have a lot of switch capacitor circuit. Basically means you have two capacitors.
Resistors.
Yes. And then you close a switch between them, and right? So this is the worst thing you can do. You get all the switch injection noise, right, in the process. And
the way charge base is no switch cap.
Yeah. So switch cap circuits, they will be noisy, they will be power hungry, because effectively you implement resistors, right?
Yes,
this means you make, right, you still have Ohm's law, and you get the noise and you get the power dissipation of resistors. What's the point of doing it? So you're better off building what's called charge redistribution circuits, in which, in this case, you have another capacitor that couples in the same node, and you drive it from both sides. So the left side of the capacitor here is driven by the APS output, right? And the other capacitor's left terminal, that is now driven by a global signal. So you have a global signal here, which now you can time, right? And now what we can do is you can vary the threshold, right? Because at the time when you close this switch, you ensure that this voltage is, say, at some reference. Let's call that, right? So let's say, what do you call this again?
What?
We call it VREF.
VREF?
Yeah.
VREF.
Okay, VREF. Very good. Yes. Okay. So now VREF would be something that would be in the middle, right? A default. When we do the reset, so we do the reset, right? This with charge distribution. So here now, and by the way, this coupling capacitor is typically much smaller than the single capacitor, because with this charge distribution, what's the principle of charge distribution? When you have two capacitors, you drive them. I think it's fine. I can write it here, right? So against this one, so the principle of charge distribution is very simple. You have two capacitors, let's call them C1 and C2. So the voltage that you have up here, so here you have Vin, so V1 is the input, and V2 is the another input. So the charge you have on this node is simply a voltage division, right, of these two capacitors. It would be C1 times V1 plus C2 times V2 divided by C1 plus C2 plus an offset, right?
So there's delta V1, delta V2, not V.
Yeah, that's why you have V off, yes.
These are all delta V's, right?
Yeah, that's okay. I agree. So you can even better say that the change of voltage. Yeah, so you can. Yeah, the whole point is the offset cancels out when you take the difference, right? So when you take a difference between, so yeah, this offset is whatever charge you have there initially, right? So this is the voltage you have at any point in time, and the offset would be very slowly time varying due to whatever one ref noise, right? So yes, if you do now a difference between, so now you have delta V1 and delta V2. So then indeed the offset is cancelled out, and you have just C1 delta V1 plus C2 delta V2, right? Yeah. So the change in your voltage is proportional to the weighted sum, the weighted average, right, of the changes of the two inputs. One is the change that you have intensity, what you care about, but the other is and you can control this in the sequence, is the reference. And now what you can do is at this point in time here, right, is the reference voltage. That is right. If now you bring it high and then low and then back at zero, right? So when the reference is higher, right, effectively what you're doing is now you're now you're lowering, right, the reference. And when the threshold and when the reference voltage is lower, now you're increasing the threshold, right? So in this case, and you define the epsilon, you define
that zone. What is going that zone
or the actual
noise and jitter and all kinds of
so you have a direct control, very precise control of the delta intensity threshold. The threshold, yes. A positive negative threshold, and you can change it, right? In fact, what we meant to do with Raj, in fact, that was a wonderful project. We even had a way of doing a 6-bit AD conversion by having a ramped staircase that we can do here. Actually, we're still testing this, right? It's so free.
But you have to apply these pulses at the row level, row by row. Right?
Yes. So for every row, you have to do this sequence up.
Yeah. So the pixels sample themselves in row parallel way.
So it'll be a little complicated, but not totally impossible. If this entire scheme by which we're doing all these operations is self-timed, we can use asynchronous circuits.
Yes.
There's nothing here, well, other than the integration that is taking place from one point to the other point, right? There's nothing strictly important about the time difference.
There's no clock.
Yes. Yeah, there's no clock. There's no need for a clock. So we can speed up this process as fast as the amplifier gets, right?
That's one huge drawback, though, that it only has a linear dynamic range of this voltage.
Oh, no, yeah. But now, okay, so this was all what we did with Udian Malik, Mike Chi, Mark Cloud, etc. Right? So this was Hopkins. Now with Raj, we took a step. Okay, so let me actually just. So actually a few quick things here. We replace the. So this for the amplifier, we turn it into the same circuit that Raj actually showed during the tutorial, right? Is this NMOS inverting amplifier, right? So that's all we have here. And the switch, of course, is in NMOS. And then this goes on the periphery, right? This is the output. The periphery, again, you have the current source, right? And then here you would measure the voltage, right? This is your comparison. You get a bit that comes out here. There's several problems with this. Well, first of all, there's not much gain here, and you may actually want to put some cascode here if you wanted to, right? But also, there's a lot of power being consumed in the process because this line needs to swing. You have this long line that goes through all the pixels, and this line has to swing all the way between ground and VDD, right? As a decision is being made, right? So you get all the CV squared energy of the line, C the line, right? So the line capacitance, which can be hundreds of femtofarads, right, gives you now hundreds of femtojoules of energy just each time you do this. Of course, it's very power angry, right? But the other thing, as Toby is saying, is that this is still frame-based because you have this linear integration, right? Each time each time you reset a pixel, and then you integrate over one frame. You can't just, if you vary the frame, this will change your gain. Maybe that's a good thing. You can actually vary the frame dynamically and have a different gain if you want to. But let's go back to the spirit of dynamic vision sensors. So first of all, we forget about reset. So now let me actually amend this circuit. Actually, before I do that, let me just show. I did talk about this, right?
Gert,
yes.
by changing that, you can change you do gain control.
Yeah. Yes. Yeah. I mean, this was great. That's great, but I don't agree with what Toby's saying. This is not event driven because all you do here is you have a certain frame rate at each time. The difference between your normal APS, which you can still use, the APS output. You can just have your events out. That's what we did at that time, right? You can get events out and you decide on the periphery, you decide, hey, nothing happened, just ignore it. And so any processing by which you register the events and send them out, communicate, right? That is now a synchronous thing. Right?
So to continue on that and say that this is not really, you can do gain control either by doing temporal gain control, local gain control, or by doing spatial gain control. You can add 4 capacitors to the pixels and play a game with charge redistribution, find the mean, and then do completely spatial local gain control using charge-based circuits, period. And that has been done.
Oh, I forgot to add a little more here, right?
There is nothing wrong with the architecture in terms of local gain control. All you need to do, add capacitors to neighbors, do some charge redistribution, and you get local gain control. And staying in the charge domain.
Yeah. In any case, yeah, so this was the pixel that's also shown here, right? They were compact and we were able to condense, right, quite a bit of functionality in one chip. It was very power hungry though. This chip consumed, in fact, it was a little embarrassing. We had a static power consumed on the periphery, and we could have easily fixed that by making the dynamic circuits. But so that's why this was milliwatts. Right? It was milliwatts of power.
Show the next one. The next one.
Okay, yeah, the next one. So now, right? So yeah, here this scheme assumed frames, which means you have each time you fully reset your pixel. In fact, reset the pixel by when you do this readout, then you do the reset, right? The reset is then done both. The reset is done here, right? Both this line here, but also you can reset the pixel here with the switch, right? And that will then implement this switch here, right? So that's how you reset your integrator. But that.
I'm going to show another slide.
Yeah.
Next one.
Next one. Okay, so here's the different portion, right? So we still have, right? So this is what we did with the glass. So we still have our active pixel sensor. We actually got rid of the readout. We didn't. I'm not sure this was a good thing to do, by the way. We may want to put the buffer back, because there was issues. This thing had a little issue.
Yes. You need the buffer, add the transistor. Yes.
Yeah, we need some impedance control, right?
Right.
So this is too high impedance at low intensities, and we observed that at low intensities this thing is a problem, but at high intensity everything is perfect, right? But so we may want to put the buffer back, and it's okay because the buffer you only drive it only when the row is selected, and you don't even have the buffer. Doesn't even require a readout, so we can get rid of the huge capacity you have for readout. You just have the local buffer, right? But only once you activate this row, you want to have this buffer active, and then it drives, right, this capacitor. So the same capacitors you have up here, except we figure out, hey, wait a minute, we can actually use the same diffusion, right? The well
diffusion,
right? Or this is just diffusion, right? For improving capacitor too. Here's a MOSFET. The MOSFET has your diffusion, right? And then the gate over it. So actually we have actually great fill. So 33% fill factor. Only the fact that 3 of the transistors share the same, I guess, your N diffusion in the P substrate that is photosensitive. Right? So this is a photodetector this is different from the local bipolar. So the vertical bipolar, right?
Don't even talk about that. Yeah,
Don't even
that's
talk about,
nuts,
yes.
yeah.
Yeah, but it's very simple. Very simple, the simplest.
Without noise. Yeah.
Yeah, this gives gain and all that, but it's bigger. So yeah, so the very simple structure here is as shown here, right? So any source or drain of a NMOS resistor is actually photosensitive. Light that shines over it will give you a photocurrent. In fact, that's what we call leakage. So, right? This is the limit. That's the reason why you cannot go subthreshold down to femtoamps, because you have a dark current at a femtoamp level that will just give you that dark current. In this case, the actual light that comes in will give you not femtoamps, but gives you picoamps or nanoamps of current. So that's what you have on every source or drain of a resistor. So might as well use it, and here use it for doing your capacitors as well as for this switch.
By removing the follower there, you could do this trick where you get more efficiency.
And it probably should.
Yep.
Sharing.
That's really why you did that.
Yeah.
But essentially, it's a bad idea. In modern technologies, you get 3 caps and multiple layers.
Yeah.
You can do fantastic stuff.
We
So
would prefer to have like a HD min cap there instead of the MOS cap.
Yeah, this was just the convenience because.
Also, you have the mismatch, the threshold mismatch between those caps, right?
Yeah, the MOS caps were medium threshold.
No, threshold doesn't matter. Threshold doesn't matter here.
It still matters pixel to pixel because each pixel will have a different threshold for that FET, right? Won't it?
no.
The threshold, no.
Yeah, as long as it's in the right region where it's depleted.
Once you are above threshold of depletion, whatever you're done.
Yeah, so you still measure, again, we only measure differences in voltage, right? So the C times delta V is still preserved no matter what the threshold of this device is.
But we don't have any geometry is really what matters there.
Yeah.
And poly thickness.
But the MOS cap reduce the range of the.
Yes.
Yes.
Right.
Yeah, there's many things you can improve.
The proper bias. You have to keep it above threshold, whatever.
That was the hard part.
Yeah.
Okay, a few more changes. So we can still operate this device, the reset of the APS, if you want, in a linear domain, the APS mode. But now we can go back to the log mode, in which we just have a constant bias on the gate. Then you say, wait a minute.
Yeah.
But now you get a threshold variations, right? The threshold that'll give you fixed pattern noise.
Yes.
No, because this as a computing temporal differences, it's fine. Again, this offset that you have here is just amortized along with the offset of this amplifier here. It's all fine, right? So the CDS operation will remove the offset here as well as over there.
But are those MOS caps operated in accumulation or inversion?
In inversion.
Inversion.
In inversion.
So don't they have then the inversion offset?
Yeah. Well, we just operate them in a strong inversion.
Strong inversion.
Yeah, but they still have that 10 millivolts of inversion offset. Maybe I'm incorrect about this. It doesn't matter, right? As long as
So you're saying that the capacitance is something like this, right? And because whatever it's
You assume that voltage, the common mode voltage is such that they can stay.
We have to discuss it later.
Yeah.
The inverting point of the begin should be above the threshold of the.
Exactly. That's it.
Could we try to use the last 10 minutes to try to get to the design of the actual?
Okay, yes, and I do want to get, exactly, I want to get, okay, so add the APS back in here, right, or just not the APS, some buffer here, we can use better capacitors, of course.
Yeah.
But still, there are a few more additions here.
Right.
Right, so now we made it truly event driven in that only when you detect a change above plus epsilon or minus epsilon, only then do you want to reset the pixel. So whereas before here, right, for every frame or every time you visit it, you would reset, and then you basically you're forced to accept an event even if there's none, and that was not very You can argue that was not a great thing to do. Although, strictly speaking, you're still measuring temporal differences, but it's not really event-driven in the sense that where you
don't memorize.
You don't memorize from the last,
no,
right? But now you can do it because only when this operation here identifies, yes, you're above or below the threshold, only then do you want to reset the pixel. And that's accomplished by having an additional line here, right? By which, so you have the feedback. The feedback tells you, hey, what is your voltage? What is the output? Is it
You drive that from the periphery.
Yes.
You need a good follower in the periphery that burns power, but it's only
No, what is not shown here is, so actually, there's a lot of good stuff here.
You don't show the peripheral, which is.
No, but actually, in fact, the greatest part of this circuit, the reason why it's 6 picojoule per event is not to do with the pixel. Well, there's a good pixel, but
It has to do
it's
with
actually
the
about the periphery, how we did, right?
Exactly.
And I do want to spend a little bit of time on explaining what we did to the periphery.
Yes. Is there another slide?
I don't have it
I
here,
just want to bring up.
but I'll do it on the whiteboard. Yes.
One major problem with this circuit as it's strong is you're using an NMOS switch, which is gonna leak a lot when you shine bright lights. It's gonna have a lot, very bad shutter efficiency.
Well, yeah, you want to make sure that all this is.
Yeah, but even if you cover it, it's gonna have very bad shutter efficiency because stuff's gonna leak to it. It is.
It's still
Yes.
just like measured in the world.
In future cameras, event-based cameras, whatever, it's gonna be face to face, and so that
I'm
will see
saying that this
nothing.
is gonna be a showstopper for the 130.
I know, Toby, I know, Toby, but the 130 is
So-
a
so right,
good
measure-
example.
We measured this, right? So we're very careful. Rush was extremely careful in the layout.
Yeah.
And so have metal kind of shielding and.
Yeah,
we
but
didn't-
if
yeah,
it's
at least
taken
we didn't-
outside, it won't work.
130
No, no.
is not really 130 for those who have done this, is 180.
Actually, this worked very well outside, not in the darker room. Yeah, the lower light we had.
Yeah, exactly. This was 180, even worse.
Okay, anyway, go ahead.
And actually, yeah, this worked.
This
Bombarded with light,
This 180.
180, yeah.
Yes.
180. You bombard it with light, there was no issue there. You get beautiful crisp. I mean, it looks okay if you look at
It's
this.
okay, very well.
I mean, it looks clean, right? There's no fixed pattern noise. You can get nice skin outfits. And you can, right? So there's no pixel, there's no, right? Because owing to the CDS nature, right? You get quite clean events. You can change the threshold, right? It was great at high intensity. We're still working on, and so hopefully we can fix the low intensity by just adding a buffer there, right?
Yeah.
But yeah, that's basically what we do here.
We have low mismatch and low bandwidth.
Yeah.
So
Yeah. But I do want to get at the efficiency. Why is it just 6 picojoules per event? Where's power being consumed here? There's no power being consumed here because this is naturally the light comes in, right? In fact, this is a way of generating charge if you want.
Yes.
This is like a
CCD.
or yeah, this
So the power is in the clock.
it's a solar cell, right? Yeah. Yeah, you can even basically you can even establish energy if you want it from this like principle.
it is consuming power, right? Just very little.
Yeah, outside in the sunlight, maybe this. Yeah, I think it's that. So you still have the readout here, but now you have this additional circuit that okay, you do the sensing. The sensing here will be run on this circuit, which I said is not great because you get CV squared, C line V squared of energy each time this energy be made.
Yeah.
So how can you avoid CV squared?
How do you
Energy.
avoid? You can do that.
Get rid of V, right? Yes, how do you get rid of
Energy
V?
recycling if you want.
How do you get rid of V? You use voltage clamp, right? The verse of the principle. You just voltage clamp. So we have a circuit here that voltage clamps the sense line continuously through all the rows that are being selected, right? And how do you make a simple voltage clamp?
Cascode.
A cascode, thank you, Christoph. Yes. So we have this cascode, not op-amp.
Okay.
I'd actually show the circuit here. Here's a bit more room. Yeah, there we go. Yeah, so this, right? So instead of this circuit, here's your right? In the pixel, you have this is right where your active circuits.
Gert, from remotely, you can't see this anymore. You need to put this on the right side of the board.
Okay, thank you. All right. Fine, let me just edit here. Is it good?
Yes, we can
Let's
see
edit.
you there on the board too.
We're good. So we get rid of CV squared line by doing a a voltage clamp here. So the periphery, right? We go, I guess we still have our PMOS. If I cascode the PMOS. Cascode basically means you don't just, a single transistor will give you an output current that is decent, right, on the drain, but you still have drain conductance, right? As the voltage changes on the drain, the current will be modulated, right?
A single transistor current conveyor.
And so, yes, exactly. So a single transistor, a conveyor basically means, in addition to your common source thing,
Common
right?
gate. You have common gate.
So now you have the common gate buffer, and this is called a cascode or current conveyor.
One gate current conveyor, yes.
Yes. And very simple, because the second element here will fix, so assuming the current, right, as the current flows, the same current must flow through both resistors. And so that basically means the gate to source voltage must be constant, more or less, the first order. So the second resistor ensures that by making its source constant, it fixes the drain of the other one, right? And effectively that gives you an improvement in gain. That's how the output conductance becomes less, right? And that the principle, this gives you very high gain. Gain here basically means almost constant current output, independent of the voltage here. Why is it gain? That basically means you get a greater swing in voltage, right, for a small change in current that you have up here, right? So give you greater swing. But we still want to.
You're missing some stuff. Are you still need to add FETs or anything?
Yeah, of course. So now we add to make it full, right? So now we're going to do this.
Just one NMOS.
NMOS or PMOS?
No, two.
Oh,
No, one
the
PMOS.
pixel, the NMOS, the pixel.
Yes, we do this way, right? This was
Oh, okay, that's for the leakage.
Yeah. So we have a full, right? So here's your output, and the output in the periphery can swing. That's fine because there you have low capacitance, right? That's fine. In fact, we can't swing too much here because if you swing too much here, this will bring those transistors in the linear region, which means that we will lose all this cascode operation. So we have another trick here. We have a circuit here that will clamp the voltage, right? And retain the voltage here. Can you still see it? Yeah. It will, right? It will clamp the voltage such that the output on a cascode here, and a cascoded inverting amplifier, will swing not any more than what is allowed for all transistors to stay in the saturation region, right? In linear G, that's where they all beautifully give very high gain. So this circuit here just ensures that we still get high gain here, right? And this cascode works beautifully. Right? Now, let me see.
Gert,
yes,
Gert, you have a very fine circuit there, but the margin is too small to contain it for the outsiders.
Yes, you can see it, right? I think you can see it. Can you see it on the?
Yes, barely.
No, it's.
Read the paper.
Okay, maybe do this one a bit more. I think it's fine, right? You see it. You see plenty. It's fine.
Oh, that's better. Thank you. Thank you very much. That helps.
It may also want to increase your window size. Anyway, so you just have constant biases here. Now, what is this guy doing here? Because in principle, you say, hey, wait a minute. This amplifier, normally for the amplifier, we have the NMOS of your amplifier in the pixel. You time multiplex its output. And then you have the cascode up here, and then the NMOS cascode, and then you have the PMOS cascode up there, right? Why do we add this additional element here? That was necessary to ensure that your cascode is always operating in its linear, in its saturated region. Because otherwise, depending on much, if you have less or more current here, right, you would this would swing, right? This means for ensuring that the voltage here will not change, because this bias that is set here by this additional, and the current, by the way, so you have basically what you have here is like 10 nanoamps or 100 nanoamps. What was it again, Raj? So you have 100 nanoamps of current here, right, to the PMOSes. This offset.
That's amplified over 250. So,
yeah, per column.
Yes.
Yes,
per column.
Yes, per column.
Yes, and how much current flows in the bottom one? It's like
20 nano.
20 nano. Right, so that basically means this at the threshold a little different, but again, we don't care about the threshold because threshold is something that we, as long as the threshold doesn't change, we're good. So this accomplishes that effectively clamping this voltage now, and it only changes by
We're finished.
a few kT/Q, right? I think we're done. Yeah.
So we're meeting outside for the outdoor group before,
Same way.
so you can have the room as long as you want.
We're done.
Oh, but we need the Zoom though.
Yes.
No, we're done.
We'll get
We'll
that,
get
yes. So yeah, we can have more questions, more discussions in the room next door.
Okay, so
So bottom line is, this is very efficient for clamping the voltage. The other circuits here that can do the encoding, but now with the new asynchronous tools, why don't we can do all this asynchronous, right? There's nothing in the circuit that requires a clock, and we can just self-time it. Now it's all self-timed because we no longer are innovating over a certain frame.
And, I think, yeah, just to finish again, I think this is fantastic. This was a fantastic tutorial. Also, pay attention on the periphery now, on the roads, on forward. What you ask is like 3 or 4 transistors. So you can actually do that. You can make a very thin pixel if you want to, and also low power. And I think this is a good candidate for the group. And when I asked Raj to really complete this workshop this year, I read his paper multiple times on Gert's, and I thought it was really very nice work that you guys did. And so I think this is really a good starting point.
Okay, so but today we're going to talk about something very different on AR, AR system.
Yeah, here's the family too.
So we have divided the talk in 3 parts. I'm gonna take care of the first one. Teresa will then present the second part. And then the last one is very quick, just a review of the present projects that we have with emerging devices. So the talk today is about emerging devices in neuromorphic systems. And to start with, I will try to do a quick introduction about the memristor concept and how to exploit it to implement spike time independent plasticity.
And Bernabe, if you actually point with the mouse on the computer, it's much better because it gets recorded. It gets recorded on the Zoom.
Actually, this.
Yeah, that pointer.
I cannot change this one.
On your computer and turn on the laser, it's much better.
Okay.
Yeah, if you could turn on the laser.
This one is working.
If you can just turn on the laser within your presentation. If you have one.
I think that's fine. You have the
In the presentation, how do I do that?
Oh, you can see here. You're sharing your screen, so you have to use PowerPoint. You move this. Here, if you move this.
Use your laptop mouse, yeah.
Yeah, I'm using my laptop.
Because these people are.
Turn on the laser there with right click. Want me to help you?
Okay,
much better.
Okay,
perfect.
Okay, so the memristor. If you ever take a circuit theory class, the first lecture is explaining you the 3 basic elements: the capacitor, the resistor, and the inductor.
No, he doesn't listen.
Okay. Yeah, I'm sorry, I'm too old. So when you take the first lecture of a circuit theory class, this would be like the first lecture. No, they tell you, okay, there are 3 basic elements: capacitor, resistor, and inductor. And there are 4 basic quantities: no, the voltage, the current, the charge, which is the integral of the current, and they also define the flux, which is the integral of the voltage. Then the relationship between voltage and current gives you the resistor, because in a resistor, the resistance is a ratio between the voltage and the current. And you can make it linear or nonlinear. Here it is expressed with small differential quantities, so it is in general nonlinear. For the capacitor, you relate voltage and charge, and for the inductor, you relate the current and the flux. But if you take Leon Chua's, when I was an undergraduate student in my circuit theory class, we used Chua's book, and he drew this graph, and he said there should be another element here, which is not there. You cannot go to the store and buy it, which relates the charge and the flux. And then he postulated the existence of a memristor, which is what he presented in this paper, 1971. And he actually built a memristor with artificially with op-amps and active components, and studied the theoretical behavior that this device would have if it existed, and wrote a series of papers, and then it evolved and so on. But that's it, and he wrote many nice textbooks with all this insight, but it was never used until in 2008. There was a paper by Strukov and Williams from HP Labs that said, I didn't put the title here. The missing memristor found, which apparently was a device that not exactly, but somehow was following this behavior that Chua postulated in 1971. And the interesting thing about this device is that it was an oxide. It was an oxide that you can build at the intersection of two metal lines. So you have whatever CMOS technology or whatever microchip technology you have at the intersection of two metal lines. If you have this type of oxide, you could have this nanoscale device, because in modern technologies, the metal lines can be, nowadays we are talking 5 nanometers, 2 nanometers, 3 nanometers. And theoretically, this behavior could be found at the intersection of two metal lines. So it was a very nice discovery, at least hope that one could make this missing circuit element, because the interesting property of this circuit element is that it behaves like a resistor, but with memory. You could change the memory, you turn off your circuit or whatever, and when you turn it on, you recover the last resistor. So it could be a memory, and actually it could be an analog memory, which makes it even more interesting. But this was the hope and the expectation. Now we are almost 20 years after, and still memristors are not mainstream in industry because there are many issues. But anyway, this was what happened at that time. And initially it was hypothesized that the behavior inside was working like if this is the oxide. So there were like two regions, a high resistance region and a low resistance region. And then when you apply voltage or direct current through it, this wall would move and change the overall resistance because you have two resistances in series, one larger and one smaller. And when you move this wall, the resistance would change. And then when you disconnect the voltage, the wall would stay at the same place. And this would be the memory. But later on, it was found when people start making experiments and modeling and studying the behavior inside, it was found that this wall model was not very precise. That in practice, what was happening is that they were building up some filaments in the oxide that were conductive filaments or traps, chains of traps that would allow a conducting path between the two metal plates. And that phenomenon was the one responsible for the change of resistance between the two electrodes. And you could have one filament, two filaments, thicker filaments, thinner filaments, and so on. And these filaments were reversible. You could, if you do it carefully, because you were actually starting to break the oxide. So when you apply a high voltage too long time, you will break the oxide and you lose your device. But if you limit the current, then these filaments would build up very carefully. You stop them at some point, and then you could actually reverse it. By reversing the voltage, you would dilute the tip of the filament, and then the resistance would go high again, and then you could play, change the resistance up and down and so on. So shortly after Chu published his paper, we started playing around with this concept now and starting doing simulations. And we came up with a very simple model that you can see here. which basically you can see that if you have a device like this, which is a memristor, these are two symbols that were used in the literature. And we have the voltage across the memristor and the current across the memristor. You see here that it is related by a conductance. And this conductance depends on, well, I also put here the voltage, because in general, the memristor is nonlinear. No, it doesn't, because a linear memristor would degrade into a resistance, automatically. So it has to be nonlinear. But I put here, you can see here this parameter W, which is some kind of structural parameter that you can consider inside your device that changes the resistance or the conductance. And when you disconnect your voltage and current and so on, this parameter will stay there. It is non-volatile until the next time you use it. And in general, one can use this very simple differential equation that changes the value of this parameter, that changes with the voltage applied. And also it has this term to limit this parameter between a minimum and a maximum. So it's a very simple equation. This F here is given by this curve, where you have a central region between two thresholds where the derivative of this parameter will not change. So if you operate your device between these two thresholds, then the resistance will remain the same. But if you go beyond this, then the W will increase. And if you operate in this region below this negative threshold, then the derivative will be negative and the W will decrease. And this will change your conductance in general. So you could have, and there are plenty of devices. No, if you look into the literature, there are plenty of devices. The ones that we have used most are the oxide-based devices, which are called resistive RAM, that you have programmable conductances. But lately, we're also working with FTJs, ferroelectric tunneling junctions, and they are more like diodes. So you have tunneling diodes, and you tune the curve of the diode. And it's also non-volatile, and you can tune the tunneling current and so on. But in general, from now on, we will consider this type, the resistive RAM. So in general, the good properties are that we can make dense, non-volatile memory. They are CMOS compatible. This is very interesting because it is an oxide. It's actually typically it's hafnium oxide, which is the one used for CMOS. So you can stack many layers of these memristors between metal lines on whatever, as many layers as your technology allows, so you could eventually stack, I don't know, 10, 20 layers of these devices. You could use online learning because, as I will explain later, by applying voltages and current through them, the parameter will change. So you can come up with learning rules that will change these conductances, which ultimately are the weights of your neural network, in neural networks in general. Although people typically use them as just memory. But we are neuromorphs, so we want to build neuromorphic systems. And it's very easy to exploit bio-inspired spiking circuits. And this is how we came up with this spike timing dependent plasticity learning. So what is spike timing dependent plasticity? Who does not know what is spike timing dependent plasticity? You're lying. Okay. Okay.
Forward this.
No. There are two people that want to know what it is.
Well, I'll go very quickly. So in biology, when you have two neurons that are connected by a synapse that has a certain strength, so that strength implies how the presynaptic neuron affects the postsynaptic neuron. So when this one transmits a spike like this, it looks like this, then it will accumulate a charge in the postsynaptic neuron that is proportional to the strength of this connection, this synaptic connection. And then B and Poe, they measured that as a function of the timing between the spike generated by the presynaptic neuron and the spike produced by the postsynaptic neuron sometime later or before. And they measured the correlation between the change of that weight and the difference in timing between the presynaptic spike and the postsynaptic spike. And they found out that if this difference in timing is positive, so the synaptic spike happens after the pre, then this connection is important because the pre-spike affects the post-spike. So this connection is important. So this weight needs to be increased. And actually, if the timing is very close, the change of the strength is larger. But if it is the opposite, the post happens before the pre, then this post had nothing to do with the pre. So this connection is not meaningful and needs to be depressed.
Because this is for a excitatory synapse.
Yes, well, if you normalize, then it is multiplicative. It depends on.
Anyway, it's just the concept of causality.
Yeah, the concept is more or less that.
I think you can also do like negative pulses, and based on the time, you can also do inhibitory responses instead of.
Yeah, you can have the weight can be positive or negative, and you have anti-STP, and yeah, you have many variations. Yeah, but the basics idea is this. So at the end, you have a plot like this, no? Depending on the delta t between the pre and the post, but between the post and minus the pre, the difference in timing, you increase the weight, and otherwise you depress. And this is what happens in biology. Now, you can do that with memristors. You can think that you have a memristor between this inside of the presynaptic cell and this inside of the postsynaptic cell, and you consider the same equations that I showed you before for this memristor, and you consider spiking signals both in V1 and in V2, in the presynaptic neuron and in the postsynaptic neuron. You consider waveforms that look like this, so like this. And here, for example, we can see the situation of pre happening before the post. Then you have here the pre, afterwards you have the post. So the difference between that the memristor will see is V2 minus V1, which is the difference between these two waveforms, which looks more or less like this. And you can see that when delta t is positive, there is a region that may be larger than the threshold that I showed you a few slides back. This threshold here, the positive threshold, which makes the memristor increase the weight. And if you do the opposite, you put the post before the pre and you compute the difference between the two signals, then there is a time where the voltage of the memristor becomes below the negative threshold. So it will make the resistance to decrease. So at the end, if you do the math, you will end up with the same curve in the change of the weight that was shown in biology. So this is very interesting because we can use memristors. We can use memristors with spikes like these to do spike timing dependent plasticity. And actually you can play with the waveforms of the spikes. For example, this is the one I explained. You get this function, but if you change the spike shape, you get different learning functions. And if you make very exotic spikes, then you can also make very exotic learning rules, which actually also happen. These rules like this, they also appear in biology. And you can engineer your learning rule by playing with the spikes and using neurons. So, and the way to build it, yes.
What are the lower bounds of the weights then?
Sorry?
What are the upper and lower bounds of the weights in that?
Well, here
0 and 1 arbitrarily, or is it?
That depends on the physics of your device. So
in your first slide, you were showing that there is this limiting process, right?
Yeah. So there is a maximum and a minimum for each device, which changes also from device to device a lot. But in general, it is bounded. But it depends on each device. Typically, for hafnium oxide memristors, we are talking minimum resistance 10 kilo ohm, maximum 100 kilo ohms.
For a chat, roughly.
Yeah, roughly. There are many devices. There are many devices, and people play with stacks of oxide layers. Some people, I have seen papers that show the high resistance is in the range of mega ohm, and the low resistance is 100 kilo ohms. Yeah. Normally, a good memristor can give you a factor of 10 between the high and the low. But ideally, we would like to have like 3 orders of magnitude to build good circuit. But in practice, we are typically in 1 order of magnitude between min and max. Now, how can you build spiking neural networks that do STDP? It's very simple. You just need to make a neuron that whenever it fires a spike forward, it will also fire the same spike backwards. And then each memristor here will be exposed to the presynaptic spike as well as to the postsynaptic spike later on. And then it will obey this STDP learning rule that I explained before. So this is the only thing that you need to make. And it is fully asynchronous. This is an example circuit that would do the job. Well, of course, you need here some circuit that will generate the waveform that you want. But in general, this is all you need. And then you can assemble. And here we are showing 2 layers, one after the other. And then you can make, here, for example, I'm illustrating an example with positive and negative weights. This is, well, it's the schematic is simplified because actually you need 2 lines, one for the positive neurons and another line for the negative neurons that will be collected at the destination neuron. One will contribute positively to the integral of the neuron, and the other line will contribute negatively to the integral. But this is a circuit that you can build. And then you can make competition between the neuron just by typical inhibitory resistive, fully connected feedback network, like the Hopfield network, for example, that do inhibition in feedback to make competition. So this way you can make like a 1-layer perceptron with competition at the output. And in these papers, we have circuits that you can download and play with them in Spectra. And here, the shapes that we are using is this shape. So we have a high positive pulse, short in time, with a long tail that is negative. And this will do the job.
But now you didn't tell us why resistors would be better than transistors.
Or floating gate.
Well,
Floating gates.
I didn't say why they. I didn't say that it should be better.
No, I mean, I guess simpler to make and also denser.
They are not better right now. Right now, you have them, you can play with them. The interesting thing is that you can put them on top. So you can, in your CMOS chip, in the silicon part, you can make your transistors, and then on top, at the intersection of the metals, you can make your memristors. This is the only advantage, and they can be nanoscale.
And they're radiation resistant.
In general, yes. They're very tolerant to radiation in general. Because
Like floating gates.
Exactly, because in floating gates you have charges which are very sensitive to radiation. Here, it is more a structural parameter that you tune, that you change.
Which one does it need to be better than transistors? Very different devices, right?
Sorry?
What does it mean to be better?
Means one number, density contributed to square.
Yeah.
That's what it means to be better.
Well, in density, they are very dense.
They want to make memory, state holding elements. If you want to make state holding elements, you put state holding elements in a millimeter square, you count how many you have. If you can do 1,000, you are 1,000, you can do 10 qubits, which you want to get with 232 megabits of flash, then you're better. You sell flash, period.
But anyway, I'm running short of time. So here we did an experiment taking Toby's DVS recording. Toby has a very nice DVS recording of driving through Pasadena, 20 minutes of events driving. So we took that recording and we simulated using these memristor models, because at that time we didn't have physical memristors to play with. So all was just speculation. But we used this recording from Toby. We extracted 324 patches of 7x7 pixels, non-overlapping patches, and built a long chain of stimulus for this network of memristors with STDP, and just let it evolve with all these. It was, at the end, it's like 74 hours of events that you feed. This was with the help of Timothy Masquelier, who is a neuro-computational scientist, and he knows about this. He actually proposed STDP, to start with, and we collaborated with him. And then he could show that by starting with random weights in the connections at the end of the training, you could see like receptive fields that are like for orientation extraction of your input visual field. And this was done asynchronously and autonomously just by this network, no? Which is something
vertical and not like evenly distributed.
Well, because there are many verticals, yeah, because it was recording driving to Pasadena, so there were trees.
The artificial world.
Yeah, yeah. So you get a lot of verticals, yes, in one position, more to the right, more to the right, more to the left, and so on. But you can see a few diagonals, you know, and other things. I mean, it's not perfect, but more or less, this is what it learned. Now, in conventional STDP, what you have is you have your presynaptic layer or postsynaptic layer. Then you have between each pre and each post neuron, you have your synapse. And this is the learning rule that I showed you before. But people make, actually these people, Simon Thorpe and Timothy Maskelier, who were the ones that proposed STDP in the first place, computationally, you know, to do object recognition and things like that. They normally simplify the rule because they get the same result, but can compute much faster. No? And instead of this function here, they switch it to this one here. And another thing they do is that they abstract time. They just look at the order of events. So they take a system, they take all the spikes, the timing of each spike in any neuron, and make a list, and remove the time. So just look at the order. And then you can apply the same STDP rule just by looking at the order in that sequence. And this is very interesting because you can accelerate or decelerate your system, and the learning will be exactly the same. So these are simplifications that these people apply. But we wanted to use memristors. But in the first project that we had, that we were offered to use real memristors, they told us, hey, be careful, don't use them as analog memory because they're very crappy. Use them as digital mirrors, so just with the low resistance value and the high resistance value, and forget about playing with intermediate values. So it will not work. So we said, okay, then we need some STDP rule that is binary, not continuous, no? Because here you apply little changes, no, to the weights. So we started to speculate whether it was possible to use a STDP rule that would switch completely the memristor from the low to the high value with a given probability. So instead of using an STDP rule that is delta W, a small change in the weight, we use this rule, which is a probability. So whenever there is a pre and a post spike, we compute a probability to change it to 0 or to 1. And we played around with that, and then we found that it works. So we have this feature extraction layer. So we apply here stimuli. We have this feature extraction layer, and we tested both with STDP, stochastic STDP, with probability, or just a random weight to compare the behavior. And the second layer would be a classifier. Of course, if you have the best classifier in the world, it doesn't matter what you do in the first layer, it will learn whatever you teach it. So here we use a very crappy classifier, just a Hebbian classifier, to check whether STDP is helping against just random weights. And we also use homeostasis and a few other tricks, to make it work. And we discovered that yes, it will help. It will help the behavior of the full system. And here, for example, I'm showing a result. This was done on FPGA, just pure digital FPGA. If you look here at the blue line is using 1-bit memory for the weights. It is using 1-bit computational blocks everywhere, to compute. And the scale for this blue experiment, which is here, the scale is the number of neurons that you need of 1-bit neurons and 1-bit hardware that you need to get a given classification accuracy. And then you can see that you can get almost 100% accuracy with about 256 neurons. Actually, with 128, you are doing pretty well. Now, if you compare with the green one is using STDP, but with 8-bit hardware. We're using 8-bit memory, 8-bit computational blocks, 8-bit adders, 8-bit everything. And here, to get the same accuracy, this is the number of neurons for the 8-bit hardware. You need also 128 neurons, curiously. But here you have much more hardware resources. Actually, the vertical lines, this vertical lines is for the same hardware resources. No? So, for example, for 32-bit, 8-bit neurons, you need more or less the same hardware resources than for 256 1-bit neurons, more or less, in the FPGA. No? These are the resources.
Why is fewer bits better? You would imagine higher resolution can only do better.
Well, at the end, apparently what matters is the number of neurons. Because the number of neurons is similar. Here, with 128 neurons, you get this almost 98%, and here with 128, you get something more or less similar.
Were they both trained on the same methodology, the sort of mastery or methodology?
No, one is the 1-bit is stochastic STDP, and the other one is traditional STDP, with small changes in the weights.
Yeah. So to get a question, the features don't change that much when you train them both. So I'm trying.
Exactly. At the end, the weights saturate at the limits. That's right. At the end of the training process, the weights saturate at the limits. So at the end, the weights tend to be binary after learning. Yeah.
Sorry, I still don't get it. So 16 neurons, you get 100% with 1-bit, but then you get 60%.
So in 1-bit hardware, to get almost 100%, you need, for example, here 128 neurons, you get 98% accuracy. And with the 8-bit hardware, you have 128 neurons, and you get, what, 100% accuracy.
I see 16 times 8.
Yeah.
So you're using
but the hardware complexity.
1-bit neurons to get.
Yeah, but the hardware complexity, the hardware resources, for example, here for this one, 128 8-bit neurons, system needs the same hardware resources than 1024 1-bit hardware system.
Yes.
And then if you compare with pure random weights, you get these curves. So it shows that STDP is actually helping the system. And then another interesting thing is counting the spikes inside the system. So if you count all the spikes inside the system, when you are performing after learning, it turns out that this blue one, the 1-bit stochastic STDP hardware, is the most efficient. Note that this is average number of neurons average number of spikes per in the hidden layers per neuron, and this is a log scale. And this one is giving you the smallest number of spikes with great difference.
So in energy efficiency.
It's very much more energy efficiency. Exactly.
Consumes energy, and so the smaller number of spikes, you're more energy efficient.
So it's interesting. I mean, I cannot explain it, but this is what we found. Okay, so now let me switch to Teresa.
Well, so here's the first advantage of doing STTP with these devices.
The only benefit of.
But now let's see what Teresa.
Okay. So far these results are simulation results, but this is the here I'm going to present the real work that we have done designing hardware with the main registers. So this thing was done in a collaboration in two European projects in collaboration with the CIA LETI technology, and it's using this technology, which is the 130 nanometer CMOS technology, and the main registers are fabricated on top, on the back end of line of the technology, in between the two upper metals of the technology. Between the two upper metals, you can see here a crosscut of the technology. This is the CMOS part, and here in between the two, this is not working very fast. In between the two of
look at your screen.
Just look at your own screen. No, just look at your own laptop.
Yeah.
So here is where the resistors are located. But the problem in this technology is also that for programming the resistor, you need to control the maximum current that goes through the main resistor. So you need a transistor here in series always with the main resistor to limit the current, because when you are making the device conductor during the setting state and during the forming stage, the device goes to a very low resistance state, and you have to limit the current, the maximum current, otherwise you just damage the device. So this is the main constraint that in fact limits the scalability of the devices, because here we see the layout of the basic element, which is the series connection of this main resistor with the CMOS. So the area below the device cannot be used really for neurons, because you have all the area is occupied by the limiting transistor, which is right now which is what is called the 1T 1R technology, and this is the main limitation right now to really scale the technology to a really dense correction interconnectivity.
I've seen papers in TSMC where they build the resistor as part of the plug in the drain of the transistor. So the drain of the transistor, the plug that goes, the via that connects to the source and drain, they make the resistor as big as the T.
But it's still one resistor per transistor.
Yeah, it's one resistor per transistor, but it's no bigger than a transistor in this case.
No. Here the resistor is very small. This is the layout of the cell, the 1T 1R cell, which is 15 micron. But as you see, the resistor is very small. It's 200 nanometers by 200 nanometers. But the CMOS part is the largest one.
I see.
What I mean, and that's why you cannot scale very dense.
Yeah. Well, in that cross view, it doesn't seem like this, because your transistor is really on the bottom.
Yeah, the transistor is not shown actually.
Here, no, but this is the layout of the cell.
Yeah.
And you see it's 15 micron, but the main resistor is very small area here.
I see.
So
yeah, of course, if you go to 20 nanometer technology, then the transistor will be much smaller. But also your main resistor can be much smaller.
Yeah.
Unless you make it intentionally big, as big as the transistor.
Yeah, this resistor is a draw of current and is at high voltage compliance, right? That's why you can use the resistors.
Yeah, so the main idea of this of our target was to build this kind of architecture where you have CMOS neurons, and on top you could have dense connection and a matrix of devices, but you cannot do it because of the 1T 1R limitation. So this is our inspiration, which is what is called the CMOS concept, which is something that was proposed by Linares many years ago in the environment of molecular electronics. So his idea was to build neurons in CMOS below, and then a crossbar of metallic of perpendicular connection, and in between the two in the crossing of the wires you have the devices, and which is actually what you should have with what you have in the background of line technology with the resistors. But so in each, here you have your neurons. Each neuron has one input, one output, and if you have slightly and in the neurons, the inputs are connected to the vertical lines, and the output are connected vertically through this connection to the horizontal wires. And slightly tilting the crossbar, you can make that only one input is connected to one vertical line and only one output is connected to one horizontal line. So you have a fully connected layer. This is the main idea. But this is something that right now cannot be done with this technology. So in practice, what people do many times is having just an array of 1T 1R devices And in the peripheral, you have here the presynaptic neurons made in CMOS, and in the postsynaptic neurons made also in CMOS. But you end up with very elongated neurons. So what we did is what we call the pseudo-small concept, which is just converting this topology, which is what we made, which was 64 by 64 fully connected neurons, but we converted it in an 8x8 unit tiles, where in each unit tile you have one presynaptic neuron, one postsynaptic neuron, and a subarray of 8 times memristors. So this is what we did.
But why did you do that? I don't understand. What was the problem with the other thing?
Because you have a much better layout, a much more efficient layout here.
It's because of the pitch.
Because
so the memristor, the 1T1R is 3 micron by 5 micron.
Oh.
Yeah.
So the pitch is very small. So the neuron that you draw at the periphery has to have a pitch of 3
yes,
microns.
yes.
So you have to make it very thin and long, very inefficient.
Yeah, so here you have a much more compact layout and shorter corrections. And here is the unit tile. This unit tile, which is about 50 micron by 50 micron, you have one postsynaptic neuron, one presynaptic neuron, and a subarray of 8 memristors. And it's equivalent, but it's more efficient in the. So with this is the design that we did. And then in the periphery, you have decoders to select each of the presynaptic neurons, each of the postsynaptic neurons, and you can select individually each memristor also using these decoders.
And another advantage that you have is you can flip the orientation of the array, right? You can go back in the other direction.
We didn't do that, but it's something that we should have done. Yeah, but yes, this is an advantage that you can switch. But in our design, we didn't do that. We thought about it afterwards. Yeah.
After reading Gert.
Yes, the idea from your, yeah, but this is not implemented here. Yeah. So this is the layout, the first layout that we did. We see here that all the 64 by 64 array with the 4K memristor is occupying like 450 micron times 450 micron. This is a very big, and this is in fact, it's a path limited design.
What are those blocks, those red boxes? Paths?
Yes, these are the paths. These are the paths, which is the limiting really the size of and then we put some individual test structures to occupy the whole area. Yeah, but this is the main here. This is the main design here. These are test structures inside. And here is the schematic. So in our design, the presynaptic neurons are stimulated vertically, and we only process one presynaptic spike at each time. So and the idea here is that when the presynaptic neuron that is stimulated, this is the waveform that we apply. We keep all the presynaptic voltages to the same constant voltage, and in the postsynaptic neurons we also have some low impedance which keeps the voltage constant to the same voltage. So only when we apply an input spike, the corresponding line goes a little bit 300 millivolts below for some time. So a current flows through the corresponding memristors in the same column. And if this is more or less this, if the memristor is in low resistive state, a current of about 300 microamps is flowing. And if the memristor is in the opposite, in the low resistance state, it would flow about 30 microamps, and for the high resistance memristor, it would go about 3 microamps. So but good. Yeah, but for a short time.
Nanoseconds.
Yes.
Yeah, that's kilo ohms.
Yeah, this is what we apply a very low voltage, but this is what more or less for say 100 millivolts you get microamps of currents. And this is the schematic of the positive neuron. We use the resistor in a binary way, as Bernabe told. And here, what we do is like we compare the current with a current comparator, and we just threshold the current. If the current is below some reference current, then we activate a charge pump here that is just integrating a charge packet which is much lower than the real current of the resistor. Here we are doing a downscaling of the current. And this is the postsynaptic neuron. And one thing that we do is we didn't do a readout. We just put here the readout is done outside, and we can trick after each applying each spike, we see which postsynaptic neurons have reached a given voltage, and for those of them that have gone through over the threshold, then we reset the corresponding neurons. And we can trim the threshold separately for each neuron, which is something that we use afterwards, and we will see for compensating the mismatch of the neurons, of the output neurons. And here is some measurements that we did with all this is the resistance for all the main resistors in the array, the 1K, the 4K main resistors. And when you put them all in the low resistance state, this is what you get, and in the high resistance state, this is what you get. So you get a bit mismatch, but we see that this is the same, but in the current that we measure when we apply. And we see that by thresholding here with a reference current of about 10 microamps, we can distinguish perfectly the state, and we can get rid of the mismatch.
So Teresa, the bottom and the top limits are probably due to the instrumentation.
But why do they clip like that?
Exactly.
Why do they saturate?
It's current compliance.
Yeah.
Yes.
Because of the current sensitivity.
Yes.
On the PCB level.
Yes.
No.
This. This is really the system. The things in between the dotted lines are the chip, the things inside the chip, and the other things are implemented on an external FPGA. In the external FPGA, we managed to send the input spike and to do the query of the postsynaptic, see which of them have reached the threshold. And for those that reach the threshold, we just keep the memory of the output spikes. And this is the setup, the experimental setup, where this is the main resistor chips, and this is the FPGA managing the chip. And here we saw some experimental results of the stochastic binary experiment of SDP that we made on the chip. So here the structure is the same structure that Bernabe explained it, that it has two layers. The first layer is the main resistors on chip that we can keep them on random state or make some SDP learning. And the second is some basic classifier. So the experiment here was to apply 4 different patterns, the A, B, C, and D, and each pattern consists of 16 features. So the task is to learn the features of the different patterns and to learn to classify the patterns based on these features. And these are the experimental results. Here, these are simulated, and these are the experimental in this bottom plot. So what we got when the main resistors are just in random state, the classification is around.
Vertical axis? Inductance? What's the vertical axis?
The accuracy.
And the vertical bar is the accuracy, the accuracy, this is 100%.
Oh, accuracy, okay.
Yes, cannot be seen very clearly. So the accuracy is around 40% when mean and a big deviation when the memristors are in the random state. And when the memristors have been gone through the STDP, you reach just one outlier and the rest is 100% classification. So it's really making it's working. And the inference time is 200 nanoseconds, and the counting all the energy of all the things, we reach a 38 picojoules per synaptic operation, which is in 5 volts BDD. So here I summarize a comparison of the features of our chip, and here we see that we get a very low charge per operation. It's the lowest one, and we don't get the lowest energy, but we are running on 5 volts, so we could do better by going to lower voltage. And in the next project, also in collaboration with the CLNT technology, what we did was to fabricate a multi-core chip. This multi-core chip is composed of 16 of these individual cores that I already explained, but they can be vertically or horizontally connected, so that in total we have 64K 1T1R devices. The area is 5 square millimeters, and we can reconfigure the system to have 1K input neurons and 64 output neurons, or just play with all the cores independently, having 16 different layers, fully connected layers, or we can have 16 input neurons and 1K output neurons. You can reconfigure the system.
And how many bits each memristor stores here?
The bits is binary, so it's 64K bits. That's because we play them in binary mode.
Well, we had one graduate student playing with this chip, trying to make analog weights.
Yes.
And he managed to get 2 bits after struggling a lot for many months.
Yeah, but in the way that we decided deposit in the synapses is just we banana. We see we read the memristor to see if it's lower than a current or higher, and just binarize the operation. And here, for example, I show some experimental results. Here is just trying to program the memristor. We program all the memristors in the 16 different cores. And we program just binary low resistance, high resistance, and these are the patterns, the intended patterns that we did. 64 different patterns, each of one with a split around a line. So, and this is what we read. These are the real values read, just sensing the resistance. So we see that there is a big mismatch between the different cores, but this mismatch doesn't affect our operation because we binarize when reading it.
I see. So those are 2 levels, 1 or 0, right?
Yes, yes.
But if you were to do like right verify, you could probably have a much cleaner analog.
Yes, we could try, but this is something that.
Yeah. We managed to get 2 bits.
Yes, it's not so. Yeah, because at the end, the memristors are not so friendly to be analog program, because at the end is just Bernabe explained, is a conductance path that is 6 or those it's not so easy to trim it.
And then they relax.
Yes.
And there's also a relaxation effect, yes.
Yeah, but so
Which
it's
is
really the question I was saying earlier,
yes.
Commercial flash is 10 gigabits per millimeter square. You show here 12 kilobits per millimeter square. So you're really 9 orders of magnitude lower than commercial flash.
In fact, those are the ministers found before the minister.
What?
Those were the ministers found before the minister, what they were.
The
minister. Yes.
So what really affects the operation is the mismatch in the output neurons. So we did some experiment to calibrate the output neurons, and this is the something that we published in the ISCAS recently. And in our experiment, we just trimmed the threshold, the reading threshold of the different output neurons, and by trimming that, we are able to calibrate all the neurons. So that yes. And these are some experiments. In this experiment, we are just using 10 output neurons, and we are just trying to distinguish these 10 different patterns, which each one is binary also, 32 binary images that we program directly in the main registers, and this, which is extended over all the cores, but the mismatch in the values are not important here. We just calibrated the output neurons, and this is the result that we got without calibration. You get very bad results, and with calibration, the confusion matrix is that, and we got almost 100% of accuracy. So this is more.
Okay. And now in the last minutes, I'm just going to give you a quick overview of some of the projects that in European project in which we have been working recently that are related to emerging devices. Now, one of them is, for example, here and within memscales. Memscales is the same project that we developed this 16-core chip, but we also had the chance to play around with TFT devices, no? IGZO, indium gallium zinc oxide thin film transistors. So these are the curves. When you measure one single transistor, you see they have an exponential slope like CMOS transistors. And the leakage, the minimum current, this is limited by the instrumentation, because we know that these devices have really low leakage, but it is not possible to measure it, at least from the outside. So we figured out a method by building an oscillator. So we do here, we charge this capacitor, we reset it to VDD, and so we charge it all the way up to VDD, and then we have here a thin film transistor that we control the gate, and then it discharges it very slowly. And then there is a comparator here, a hysteresis comparator with a chain of inverters, and once it reaches a given threshold, the threshold of the hysteresis element, it will reset it again. And here you can see a measurement. This is a measurement of one cycle, which is 68,000 seconds. So it's 18 hours, 53 minutes. And this...
You're patient.
Yeah, well, you leave it overnight and come back. And if you compute, because we know the capacitance, this. So, well, it is an exponential. No, you see here, it is not really a discharging current. No, it is more like resistance. But the current that you have here at the end of the tail is a few attoamps in this case. And the interesting thing is that you can change, by changing the gate, you can change a lot the current over 10 order of magnitude actually.
So attoamp is how many electrons per second?
10 electrons a second.
It's about 10 or even less, 10 electrons per second at the end.
At room temperature.
Room temperature, yes. Yeah. Lab temperature.
And there's no substrate leakage, right? Is there a thin film?
No, because all this is plastic. It's isolated. There is no bulk. So you have actually these devices are very sensitive to electrostatic charge. Even during bonding, we had real nightmares for bonding because you cannot ground the substrate. Everything is floating. Normally, actually, this was fabricated by Pragmatic, and normally Pragmatic. We told them that we had a lot of issues with bonding and all that, and they said, well, we never bond them because we sell this to people that do RFID. So they make an antenna and they never have pads. They don't encapsulate everything is just wireless.
Pragmatic is a foundry.
It's a foundry,
available
yes.
through Europractice.
Yes, it's available through Europractice, and it's not expensive. They give you a little wafer like this big.
Yeah.
With all your plastic devices in there, and you can make circuits. You only have NMOS transistors. You only have NMOS and resistors.
It's like 1 micrometer. It's like huge.
It's it's in the order of micrometers. It's 1 micrometer, I believe. I'm not sure right now, but it's about 1 micrometer. Yeah, and it's really cheap. But don't package it. It's the real pain. You will destroy your devices. The wires will go away. It was a nightmare. Huh? Now with this same concept, we built a neuron. It's the same oscillator circuit, but now we use the leakage as the leakage for the neuron, and then we can make neurons that changes a lot in leakage rate. So we can have leakage rates in the rate of millihertz or in the range of megahertz. And then you can change your input patterns from megahertz to millihertz. So it's many decades, which is interesting in many applications, because normally some layers need very fast response, but when you do like very long sequences learning, especially in biology, bioimplants and so, you need very long learning sequences.
But this is essentially a current to frequency converter with organic devices.
Exactly.
With very low currents.
And we're out of time. One more thing, right? We're out of time, basically.
Yeah, we're out of time. So this is another chip that we made. This is like a chip. There's a 1 centimeter square chip that has a lot of crossbars where you can build on top any memristor that you want. So we fabricated at CMOS, and we give it away to other people that play around with memristors. Here, for example, they fabricated on top these big structures. This is a 2x2 crossbar, but there are up to the largest one was 10 by 10, I think. This is another project. This is one I mentioned about oscillatory neurons with VO2 devices. So this is like a Hopfield network. It's an IC machine, what Rajit mentioned the other day. But here we used VO2 devices. But we did a chip in which we emulated the VO2 devices. We didn't really use the VO2 devices. This was done in the project, but I'm not showing that part here. So this is just a chip that emulates the VO2 device, which is basically this hysteresis device, that you can do with just a handful of transistors. And then, but the problem was that we needed positive and negative interconnections. And to have negative, and they are interconnected, they are coupled with resistances, which are positive. So in order to be able to do negative interconnection, we came up with this idea of making a differential oscillator that has 2 phases. The positive and the negative, they are in opposite phase. And then when you connect 2 of these neurons, you can take the positive phase, connect to the negative phase of the other one, and this would have an inhibitory effect. And then you can build up a network.
Differential.
Yeah. Then we built this little 9 neuron system, which is a Hopfield network, and we could train it. Then there's another project, this SpinH, where we built, we put a memristor chip on top of CMOS chip to make an 8x8 crossbar, or with flip chip. So here is a memristor chip. And in the CMOS, we have all the 1T devices and all the selectors and everything. And this would be with flip chip. There's another interesting project. This is very interesting. This is they are really crazy. They want to build these microbots, which are 100 micrometer cube little devices with antennas and LEDs and sensing devices. And they want to fill the brain with these little microbots, and they communicate wirelessly with some device on outside. And then here outside, our role was to make a spiking neural network with ferroelectric tunneling junctions. So we designed this chip that has 279 by 64 synapses. And here, this is 1 synapse with 4 plates. On top of these plates is where you build your FTJ device. So I think this is the last one. Thank you.
Well, also we have the pipettes.
Yeah, I mean, I didn't put all the projects. I just, if you not go very quickly. Yeah,
Like putting gates could be better. Cool. So we invite the people that want to stick around and discuss these things. but otherwise maybe people want to go off and work with projects still. or-
Great beer.
Thank you, guys.
Thank you for coming late to tell us the story.
Thank you for nice public being here so late.
Wonderful.
Yeah.
Thanks.
Okay,